Great having you all here as we continue our scientific dialogue across the UWC movement. Today, we'll be diving deep into physics with our speakers Rohan Kumar, Shivam Mundra, Attila Kovacs, Jasmine Hills, Tai Huang, and Vikram Manikantan. These speakers will be walking us through their interesting, albeit complex fields, looking at quantum computing, quantum mechanics, plasma physics, astronomy, and astrophysics. Before we dive into today's sessions, I want to remind you that we will be sending out an email with details on how to register for our mentorship program, which will connect you with PhD mentors in your field. It's a great opportunity to gain research experience, direct guidance, and support from experts, and we encourage you to consider participating. You have time until the end of this week to apply. Thank you again for being here. We look forward to today's talk, and we hope you find these sessions insightful and thought-provoking. After the talk, stay tuned for a panel discussion on exploring the connections between science and humanity. We encourage you again to ask questions and engage with our speakers. Please bother them, badger them, ask them anything. You can also raise your hand and we will give you a chance to speak through the mic. And I will be chairing the first talk with our first speaker, who sits at the cutting edge where physics, mathematics, and computer science converge. Please join me in welcoming Rohan Kumar, a computer science PhD student at Yale University, where he focuses on making quantum computing more practical and robust. Rohan is an NSF graduate research and Sterling Prize Fellow with research experience spanning the University of Chicago, Oxford, and JP Morgan Chase. His work tackles one of the biggest challenges in quantum computing, noise, by designing architectures and protocols that bridge the gap between quantum hardware and algorithms. Through this interdisciplinary approach, Rohan is paving the path towards scalable, reliable quantum computers. Let's give a warm welcome to our first speaker, Rohan Kumar. Thank you very much.
Hello, everyone. Very, very excited to be here. Thank you all to the organizers for putting together what is a very, very surprisingly well-managed conference. I've never seen this size and scale from a high school organization before, so I think you guys are really lucky, and you're gonna really enjoy all the talks ahead. I personally know some of these people. I went to school with them. They're very, very smart. So you're gonna have a great time, and I would definitely stick around for everything if you have the time. All right, so I'm going to dive into the topic of my presentation today, which is on my research in quantum computing. Now, I kind of work at a specific intersection in quantum computing, but in order to understand it, you actually have to understand the sort of general landscape of quantum computing writ large. And so what I want to do for you today is give you a very high-level understanding of what quantum computing is, why you should possibly be interested in working on it, and where you could fit in. And along the way, I'll sort of touch on the kinds of things that I work on, if that sounds interesting to you. All right, so let me get started here. I think the panelists did a very good job of describing my background, but just as a recap, I'm a PhD student at Yale, working on this intersection of quantum hardware and software. I'm funded by an NSF Graduate Research Fellowship. I did my undergrad at U Chicago. And I've had some research experiences at JP Morgan, University of Oxford, and this startup called Supertech that was acquired by a quantum company called Inflection a few years ago. And I was an alumnus of UWC class of 2019 in Singapore, Dover campus. All right, so let me just not waste too much time and get straight into it. Many of you have probably not even heard of what quantum computing is at a detailed level before. Maybe I'll just give you the high-level picture here. So you may have heard that, all of the computers that you use in your day-to-day life, whether it's your laptop, whether it's even your microwave, your mobile phone, your pager, your radio, anything that you've ever used, anything that you will use for the next 5 years, is sort of based on computation using zeros and ones. We call these classical computers. The fundamental unit of an information is something called a binary digit, which is shortened to a bit, and that can take on a value of 0 and 1. And so, this is the basis of all computation. Pretty much any time you write any code, this is what it's being compiled down into. But in contrast, this is not really descriptive or indicative of what is happening at the smallest levels of physics in our universe. And in fact, like nature is inherently quantum mechanical, where you can have not just zeros and ones, but perhaps superpositions of many different states, like 0, 1, 2, 3, all at one time. And so the general question of quantum computing is, what could we do better or differently if we were able to compute with quantum mechanical systems rather than binary systems? So I don't want to get bogged down the technical detail of what this sphere is on the right. It's something called the Bloch sphere if you want to search it up. But this is sort of the high level question of what exploring the field of quantum computing is leading us to investigate. And just to motivate this a little bit further, one of the greatest physicists of all time, Richard Feynman, sort of sparked, or helped spark the initial investigation into quantum computing with this quote, which is very often cited, where he said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." So what did he mean? Well, imagine you have something like a complex molecule you see on the bottom here. This molecule is comprised of lots of atoms and links between atoms. If you sort of try and use a classical computer to simulate how this molecule behaves, you have to keep track of an exponential number of interactions between these atoms in the molecule. And the reason why is because every atom can interact in a sort of non-trivial way with every other atom, and this blows up very, very quickly. And on top of that, the kinds of interactions that you're modeling are just not inherent to the classical computer that you're using to simulate it, right? Every interaction, you have to sort of map how the interaction between two atoms will actually sort of map to a nice thing that you can actually do on your classical computer. But this is pretty inefficient, and it leads to this large overhead that makes simulating molecules very, very expensive. In contrast, if you were to try and do this on a quantum computer, since the quantum computer is inherently quantum mechanical, there are smarter ways that you can use to map this molecule to a quantum computer and use far, far fewer resources in order to understand how it evolves over time. So this is sort of the high-level idea as to why we want to try and build a quantum computer, or at least it was the initial motivation, and I'll talk about some applications soon. Okay, but you might be wondering, okay, so at a high level, we're using quantum mechanical systems to do computation. How do you actually concretely do this? Well, there are a few ways that one can realize sort of controllable quantum systems to do computation. It might help here for me to just clarify that when we talk about doing computation with quantum mechanical systems, we typically think of doing analogs to the classical bit, which are ones and zeros. And in this case, in quantum systems, if any of you are familiar with sort of very basic, quantum mechanics, which, even if you're not, that's okay. The sort of basis of a quantum bit is that you're able to not just have zeros and ones, but have sort of superpositions or combinations of them at the same time. So general quantum systems have many more than just, level 0, 1. They can have 2, 3, 4, 5. But, for quantum computing, we try and simplify our thought process a little bit. We try and just constrain ourselves to systems that we can just trap in 2 levels, either 0 or 1, and then we can manipulate the information between those 2 levels. So how do we do this? Well, there are a few ways we can do this. The first is that we can actually manufacture really, really small circuits on our own that are so small that they actually start to exhibit quantum mechanical properties. And if we want to be able to control them well, we also have to cool these circuits down to very, very, very cold temperatures until they become superconducting, which is when the electrical resistance in these materials becomes 0 due to some quantum mechanical effects. And once this happens, energy is conserved within the circuit. If you have some current in it, that energy can't really go anywhere because the resistance has gone to 0. And so you actually have a really nice model for controlling a qubit. We call these superconducting qubits, and they have to be so cold, in fact, they have to be just a few microkelvin above absolute 0, which is the coldest possible temperature that you can have in the universe. Another modality that's gaining a lot of steam these days are neutral atoms. Actually, Shivam will talk to you about this in the next talk. I highly recommend you stick around for that. So neutral atoms are exactly as they sound. They're just atoms that have an equal number of protons and electrons, and you're basically able to trap them in these large grids using very, very focused beams of light. And the quantum mechanical system that you're manipulating here are the energy levels of the outer shell of the neutral atom's electrons. So you can see that in the diagram over here on the top right. That electron can jump between a lower energy level and a higher energy level, depending on whether you excite it with a photon of a particular frequency. And when you do that, you can jump between the two levels, or you can simulate an emission down from 1 to 0. And with more complex sort of types of light, you can actually put them in superposition between the low energy state and the high energy state. Trapped ions are very, very similar to this. The only difference is that now they have a different number of protons and electrons, and so they have a net electric charge. So instead of trapping them with light, you actually trap them with an oscillating electromagnetic field. The trapped ions have actually different advantages and disadvantages to neutral atoms, even in the computation realm. That's a little bit beyond the level of this talk, so I'm not going to go too much into it. But one really interesting thing about trapped ions is that they're actually, you would think that using electromagnetic field is easy. You just sort of create a static electromagnetic field and sit the ions in the middle there. But you actually can't do that because there's this interesting principle in physics that you cannot have a three-dimensional electromagnetic field that has a constant stable point in all dimensions. And so if you are able to trap it in this dimension, it will fall off in that dimension. And so what you need to do is just have this oscillating electromagnetic field that keeps changing in order to keep that ion trapped in a fixed point. The last modality that I'm going to talk about briefly are these photonic computers. These are actually using the quantum mechanical properties of light itself to do computation. So one trivial way for you to think about how light can be quantum mechanical is in the polarization of the light. You may have learned that light can be polarized in all sorts of different directions. Generic light, let's say that's coming from a light bulb or the sun, which is kind of hitting my face right now, so I'll shift over, is sort of polarized in all directions. So it's kind of oscillating in a very, coarse mental model. It's not super reflective of reality. They're sort of oscillating this way. They're also oscillating, horizontally, side to side. They're oscillating in all sorts of different directions. The polarization of light is like a quantum mechanical phenomenon. You can sort of treat vertically polarized as being the 0 state, horizontally polarized as being the 1 state, and then, sort of gradations between the two. If I have like polarization at 45 degrees, I can sort of measure it. And when I measure it, I'll either get 0 or 1, which is horizontal or vertical. I haven't talked about measurement yet, so don't worry about that if you don't understand it. But the way that people are doing computation with photonic quantum computers at the moment is that they're actually using a much more interesting quantum mechanical phenomenon, something called a dual rail encoding of the photons. And that's basically what happens when you send a single photon through a wire, and you basically split the paths that the photon can take in two directions, and you put something in the middle. And you can basically engineer it so that that there's one photon between the two wires, but you don't know which wire it's in. And that's the superposition. It's like either in left wire means 0 or right wire means 1. And you can have superpositions of the two. And since it's only one photon, you're really talking about only one packet of information. So you've actually superposed it between the two wires. So those are some high level intuitions as to like how you can realize like a quantum equivalent of a bit in hardware. You'll notice that these are all much, much harder to implement than your classical model of like what a normal binary digit looks like, in a classical computer. In a classical computer, all you have to do is either send a high voltage or send a low voltage. And these voltages are so high that, the control electronics associated with it are very, very easy to implement, relatively speaking. In the quantum case, these are much, much harder to control. You're literally sort of manipulating individual atoms. And this is where a lot of the engineering overhead of quantum computing comes from, is actually trying to figure out how to get this control and sort of stability really, really baked well into the hardware. Okay, so let's, we looked at the very, very low level. Let's like zoom out and look at the very, very high level. What can you do with these quantum computers if you have them? Suppose I had a bunch of perfect qubits that I could manipulate however I wanted. What could I do with them? There are a bunch of algorithms that we think would be useful, and probably many, many more that we haven't even begun to discover yet. So the first that, many people in the audience may have heard of is this algorithm called Shor's algorithm. I'm going to speed up a little bit here, so I apologize if I'm unclear, but I want to make sure that we save some time for questions. Shor's algorithm is basically an algorithm to crack a cryptographic protocol called RSA. RSA is basically the basis of cryptography for much of our internet. And so if you're able to break RSA with Shor's algorithm, then either the whole internet has to change their cryptographic protocol, which we're already in the process of doing because of the threat of quantum computers, or your data will just be compromised. And in fact, what a lot of governments right now are doing is that they're storing lots of data right now, so that when quantum computers are able to crack RSA, they're able to go back in time and decrypt that information. So suppose you're like the US and like you want to find out whether Iran is like built. Okay, maybe this is like not time sensitive, but you want to figure out like what Russia's like nuclear program is doing. you can like in 2025, you can like harvest a bunch of data and you can keep that data with you, right? And in 2035, when quantum computers are able to crack RSA, I don't know whether that's true or not, you can like go back and figure out what Russia's nuclear program was doing in 2025 because you're now able to decrypt all that information. That's like an interesting little tidbit about what's going on geopolitically. There's another algorithm called Grover's algorithm, which can do the unstructured search problem faster than classical computers. So what is unstructured search? Is basically when you have no structure to your data isn't sorted in any particular way. You have no idea where data is relative to other data, but you're trying to look for a particular element with a particular property in this big data. It's like finding a needle in a haystack. Typically, no classical computer can do better than just manually searching the haystack because you have no information to work with. Very surprisingly, quantum computers can do this in square root the amount of time, which is like very, very odd. The fact that there's no structure to the data and quantum computers can still find something faster is kind of a testament to the power that is sort of dormant in these systems if we can just realize them. There are some other applications. I already talked about molecular simulation a little bit, but constrained optimization is an interesting one. A lot of problems out there can be formulated as constrained optimization problems, which are just basically a set of problems where you're trying to change a bunch of things to get some objective, or like make some objective really, really good. But you have a constraint on how you change the things. So like, for example, if you have like a stock portfolio and you say, I don't want to spend more than $3,000 investing into stocks, I also want to like minimize the probability that I lose everything, but I'm okay like also minimizing like my potential upside, and I have some like bound on that. There are all sorts of constraints you can add to like, how I want to pick my stocks, and this becomes a constrained optimization problem. And actually, theoretically, quantum computers are more efficient at solving these, although the extent to which we're still not clear because the hardware isn't quite there yet. Right, and so hinting at this, the hardware isn't quite there yet. Why is that? Well, one of the biggest problems is that these quantum systems are real physical systems that are sitting in a lab, and keeping them stable and controlling them is very, very hard. And so, you don't have a bunch of theoretically perfect qubits sitting around. You actually have these qubits that are, you can just imagine them as being in a box, and all these particles and things from the environment are flying at them. And we're basically trying to keep the box as insulated from the environment as possible, because any of these microscopic particles are also quantum mechanical, and they're going to go and disrupt what's happening in your quantum computer, right? And just to give you some context, like when we do computation on classical computers these days, our classical bit error rates are on the order of 10 to the minus 18. You can wait a very, very, very long time, trillions of times for trillions of iterations of seconds, and you won't have an error on your classical computer. But your quantum bit error rates are on the order of 10 to the minus 3, right? Like 1 part in 1,000. Right? And this is like a gigantic difference. And if we want to have practical quantum systems, we need to start being able to close the gap. Practical applications for quantum computers really only start emerging at error rates of about 10 to the minus 6 to 10 to the minus 9. So we're really at least 3 orders of magnitude off. We need to get the error rates like 1,000 times better. Thankfully, we do have a way of doing this, which is via quantum error correction, which I'll talk about in a second. But at a high level, let me just talk about how we can try and solve this problem. There are sort of two complementary approaches. We can either make the devices a lot better, the hardware a lot better. So this is sort of in the realm of physics, device engineering, optics, fabrication, right? Or we can do what my research is focused on, which is trying to use these imperfect qubits the best we can in order to get the maximal value out of them today. And if we keep doing that, then eventually, by the time our hardware becomes good enough, we'll sort of meet at this intersection point. The way I like to visualize it is that, building better hardware is like raising the floor of these quantum computers, and making the software better, or like using the qubits in a smarter way is like bringing down the ceiling. And once we have like these two curves intersect is when we have some practical advantages for quantum computers. Okay, so this slide may look a little bit technical, but it's really, what I really wanted you to focus on is like a very, very qualitative idea, which is that if you're trying to go from, in your classical computers, in your normal laptop, from playing a video game down to the level of bits, there's a large software stack that sits below that, right? From your application, which is, let's say, playing Fortnite, you have to compile it down to a bunch of like internet algorithms, which go down to a bunch of programming languages, which are then compiled down into assembly languages, which then go down to machine code, and so on and so forth. And the purpose of each layer in this stack is to literally just abstract away all the details of the stack, of the entire stack below, away from the person who wants to use it on top, so that you playing the game Fortnite doesn't have to understand how the bits are being manipulated at the low level in order to play. quantum computing has a similar sort of approach. We want to use a stack to abstract away layers, but also in our stack, we want to use the stack to minimize the effect of noise for algorithms at the top of the stack, right? So you'll see in the stack, for example, there's quantum error correction, there's error mitigation, and the pulse control, for example, near the bottom of the stack will also primarily be thinking about not just abstraction away from the gates that you want to apply, but also like how do we reduce the noise as much as possible in the pulse control when exposing it to people on the top. And so this is kind of one way you can think about the difficulty of quantum computing. You really have two goals. One is to do the same abstraction layer that classical computers are doing, and the other is just to like reduce the effect of noise. And doing both of these things together is very, very difficult, which is part of the reason why quantum computing is hard. I'm going to start going even faster, so I might skip over some slides. But just to give you a general picture, quantum error correction is, sort of the leading way that people think about solving this error problem. It's where you use multiple qubits to encode one single qubit. And just to give you a sense of, what I work on, these are the kinds of things I work on, like how do you efficiently implement these quantum error correction codes on hardware? What kind of tricks can you play to get more juice out of your device? And there's all sorts of interesting considerations here. If your qubits are only connected in a particular way, you might want to change your error correction code. If you know that your noise in your qubits looks like a particular thing rather than something else, you can use tailored error correction codes to correct those kinds of noise better than other kinds of noise. If you know you're going to run a particular algorithm, maybe the logical gates that you can implement on a particular error correction code, which means like the kind of operations you can do in the error correction code are different between error correction codes. And so if you know you have a particular algorithm you want to implement, maybe you can tailor the quantum error correction code to that algorithm. There's all sorts of interesting tricks you can play in the intersection of math, computer science, and physics. And so if you are sort of interested in any of the three, there's lots of room for you to explore different ideas. If you're a mathematician, you can come up with new error correcting codes from the ground up. If you're a physicist, you can work on the fundamental device physics, or you can even understand from a theoretical physics perspective how to tailor these error correction codes to particular kinds of physical noise. If you're a computer scientist, there are all sorts of architecture things you can think about in terms of laying out the qubits, in terms of mapping the qubits to the actual device, in terms of compiling your circuits. And they all converge. They're all mixed together. Like you need to know a little bit of physics, a little bit of math, a little bit of computer science. You can be specialized in one, but you need to have peripheral understanding of all three. And this is part of what makes me really excited about working in quantum computing, is that there's all sort of creative ideas that you can use to explore all sorts of different ideas that people haven't actually thought about before. Hold on a second. On my end, there's something blocking my screen. There we go. I fixed it. Just to give you a sense of where quantum computing is and why you should work on it, from our perspective, practical quantum computing, after many years, is finally emerging. Quantum error correction, which is a significant bottleneck that's existed for a long time, is finally becoming a reality. And we're also finally reaching a point where the physical base qubit error rates are below this threshold of error correction actually working. And so in tandem with that, we're also beginning to run the first real demonstrations of quantum applications. Some of them are even potentially showing advantages over classical computers. And on top of that, many hardware modalities are slowly reaching maturity. And these are like the examples I showed you before. And the crucial point is that in order for quantum computing to get kickstarted as a field, only one of them really needs to work, right? We'd like all of them to work so we can realize the advantages and disadvantages of all the different systems. But we're really waiting for one of them to work. And I'm sure Shivam will tell you in the next talk why neutral atoms is going to be that. But just to close out, I want to tell you why you should get involved. And here are a few points that I hope you find convincing. First of all, the potential applications to quantum computing, of quantum computing to the world are transformational. Machine learning is a hot topic these days. There's a lot of theme right now in the research community about how we can use quantum computing to do more energy efficient machine learning. Also, all the things that I discussed before, chemical design, drug discovery, optimization, and more. The other point is that quantum computing is still very early, but I think it's not too early for you to get involved. You have an opportunity to do very foundational and important things in the field if you start now. The way I like to mentally model it, and I can't promise this is a good analogy, is that if you get in 15 years early to machine learning as a high school student, then you're probably in a very good place by the time you graduate your master's or your PhD. And so if you think about it in an analogous way, you have the opportunity to do very, very impactful things in quantum computing. There's still a lot of leverage in the field because there are a lot of underexplored ideas. And I hope that you will be one of the people, kind of taking advantage of this opportunity. As I said before, it's super interdisciplinary. You can sort of have ideas across math, computer science, physics, and the intersection of the three. And so there's a lot of opportunities for creative solutions and solutions in sort of subfields that you particularly are interested in. And the last is that quantum computing is actually pretty hard. And I would argue that working on hard and potentially useful problems is always a net positive, right? Especially when you're a student. You can always move to something that is sort of, directly relevant today once you graduate. And people will respect you for having worked on the hard thing. And so I would argue also that there's very little relative loss to you working on quantum computing right now as an undergraduate or moving into your undergraduate degree. So I'd like to say thank you very much to everyone again for organizing. And if you want, it's a shameless plug, if you want more quantum science or AI explainers, feel free to follow my Substack. There's a QR code right there. Yeah, I don't know how much time you have for questions, so I'll let the organizers take over.
We have some time for questions,
Sure.
so we'll be airing some of the Q&A we've been getting from the audience.
Sure.
First of all, thank you for the great talk. One of the questions we got from the audience was, in very small things such as electrons or trapped ion, quantum mechanics hold, which is true until an observation effect is demonstrated. So this member of the audience wants to know that when you run a quantum computer for the picoseconds or whatever it is time unit, when a measurement is taken, all qubits collapse to either 0 or 1. But they want to know how you could use that to skew to the right answer. They get the highest probability in a chart, and they just hope to get this confusion clarified.
Yeah, so I think whoever asked the question is exactly on the right track intuitively. There is this issue in quantum computing. So I didn't go into the technical details because I think, it was already rushed as it is. But the person who asked the question is absolutely right. One of the challenges of designing quantum algorithms is that you cannot just simply measure the quantum state at the end of the algorithm. You can't just say, I was in a superposition of all of these different quantum states via one measurement, because you collapse the measurement. When, in quantum mechanics, when you observe a quantum state, you collapse it into classical information. But the collapse is crucially probabilistic, right? So the closer you are to 0 in superposition, the more likely you sort of collapse 0, and vice versa for 1. And so a lot of the difficulty of designing good quantum algorithms is figuring out how you can interfere the quantum states with each other, make use of superposition, to basically build up the probability of the correct answer being the highest and the probability of all the wrong answers being lower probability. And so, yes, you cannot just directly say, well, if I know that the answer is this particular quantum state, then I want to evolve to this quantum state. There's something like a little bit more subtle going on, which is partly also the reason why quantum algorithm development is so slow. Like if you think about the number of quantum algorithms that we have, that we know could give us provable advantage over classical computers, it's actually fairly small. And this is part of the reason why. Now, on the flip side, I think that this is also like not a super pessimistic piece of news for quantum computing. I think that and this might be an interesting bit of outlook for everyone, like if you can imagine being in the 1990s and not being able to run like even a single layer of a neural network in hardware because it was too computationally expensive, right? Could anyone have like provably found the action of like a foundation model and like the benefits that it could like present to society? Probably not, right? Like you can't even begin to like simulate a single layer of a neural network, right? And so my belief is that when the devices get up to scale and we're able to actually run things on the devices directly instead of simulating them, because simulating them on a classical computer is exponentially difficult, right? Otherwise, we could just do all quantum computing on a classical computer. Once we get to the scale of like quantum computers being able to actually be testable, we can run things on them, we can trust their outputs more. I think that the number of applications out there will explode. And so maybe this is like a very long journey of an answer, but I hope that sort of gives you some perspective that you're looking for.
Thank you very much. So it would appear that we currently have one of our attendees ask a question. So Nicolina, if you would like to ask your question in person, that would be wonderful.
Hello, thank you very much for the presentation. It was really interesting. First of all, I want to ask when it comes to having like practical quantum computers, which type do you think would like work the best? I think you mentioned how you're hopeful about neutral atom quantum computers, and I suppose that's because like it's literally just utilizing what we already have in nature. But I would like to more into detail. Why do you think those are that's the type that will be the most accessible one in the future? Thank you.
Okay, so just to be clear, my opinion is not that neutral atoms will be the most successful. I was joking about the next speaker saying that because he's someone I'm very close with, and he works in neutral atom devices.
Okay, sorry, thank you.
But so to answer your question, I think it's not clear. It is very true that neutral atoms have probably the most momentum right now. So if you ask a bunch of people who are in the know to place a bet, I think at this point, at least the plurality of people would say that neutral atoms would win out. One of the reasons for this is that you can actually move the atoms around during computation. This is a really, really, this was a little bit of an underappreciated fact, I think, about like 10 years ago, at least theoretically when we were thinking about these devices. I think people are really beginning to appreciate them now. One of the reasons this is useful is because it turns out that the quantum error correction codes that you can implement become much, much more powerful when you can interact qubits. You know that grid that I showed you earlier? Can't seem to pan back to it. Hold on. Oh, okay. Wait. Yeah, there you go. So this grid, if you can interact qubits that are far away from each other in the grid, rather than just the ones that are right next to each other, you can actually get quantum error correction codes that are much, much more powerful. And so when you're able to move neutral atoms around, you can actually do that. But if you're like, let's say on a superconducting circuit where it's all baked into the hardware, like in the top left here, you can't really do those interactions unless you physically build in more wires into your device, and this becomes pretty messy and more difficult from an engineering perspective. So this is like the case for neutral atoms. There are a lot of other cases for neutral atoms, and maybe Shivam will talk about it. But there are a lot of cases for the other ones as well. And typically, like, you think about the advantages or disadvantages of these systems as being at the computational level. So I think of, like, for example, superconducting qubits as having maybe low connectivity but high engineerability. You can, like, manufacture them however you'd like. You can run certain gate sets on some hardwares better than others, and that might get you better compilation overheads. I suspect, though, that a lot of this is really just noise, and really at the end of the day, the modality that wins out is going to be the one that solves one or two really, really crucial problems, which is that of quantum error correction and that of scalability. So if you can get a lot of atoms that have very, very sort of uniform quality across all of the atoms, I say atoms, sorry, qubits, maybe that's giving my bias away. But like, if you can manufacture lots and lots of qubits, and the quality of all the qubits is consistent across the entire grid, and it's pretty good, then you solved one problem. And if you can run really good error correction codes on it, you solve another problem. And I think once you solve those two problems, really the rest of it is just residue. And I think that's what's going to end up happening. Whatever wins out, that's going to be the two problems that they really solve. But it's kind of unclear right now. And I will probably write a blog post on this at some point. So if you want more details, I would recommend you look at that.
Thank you very much.
Sure.
Thank you so much for answering the question also. I think now is about as good time to introduce Shivam. Would you like to do that?
Yeah, sure. So I've sort of made a joke about this during the talk that Shivam will now sell you on neutral atoms. Actually, Shivam and I started the Physics Society at UWC Dover in Singapore back when we were, I think, like, what, 15 or 16. And since then, we've gone to, run the Physics Society together. Also, like, I handed over the University of Chicago Quantum Society to him. He is very, very sharp, one of the best physicists, up-and-coming physicists I know. I would highly recommend you stick around for his talk. He's great. So introducing the next speaker, he is an incoming Harvard PhD working on neutral atom quantum computing. He went to Chicago like me, some physics and math. He's done research at Caltech and others, which I'm sure he will be annoyed at me for forgetting now. And IIT in India. So introducing Shivam, please stick around. Thank you.
This is the first time I've met this Rohan guy. Right, I'm kidding. Yeah, great talk, Rohan. That's very good. I think I'll build on that now. Yeah, so I can share my screen. Okay, so go ahead. So yeah, like Rohan was saying, I'll be talking, kind of building on this talk, which is a great talk that introduced all of where quantum computing is at, the different modalities, kind of what the challenges are. And I'll be kind of zooming in more on the neutral atom side, like Rohan said, and kind of doing quantum technologies with atomic platforms. So firstly, yeah, thank you to the UWC Science Collective for organizing this as well. It's really well run, and I'm glad we can all share our different research and learn from each other. So quick introduction on my part. So as you've already seen, class of 2019 in UWC SCA, which is in Singapore. And I did like a 1-month internship at IIT Madras on like a quantum key distribution research internship. Then I did 2 years in the Singapore Armed Forces, which is like an interlude between my research kind of endeavors. And then, yeah, 4 years at UChicago, did a summer undergraduate research fellowship at Caltech, which I would highly recommend to, no matter where you go for undergrad, the Caltech Summer Undergraduate Research Fellowship, people from all over the world come, and there's some really cool research happening there. So if you want to find out more about that as well, you can reach out to me. And yeah, lastly, I did a 13-week research fellowship at Harvard, and now I'm starting my PhD there. So kind of the big picture, rather the point of showing this is that research can take you a lot of cool places and you can meet a lot of cool people. So yeah, you're not really like stuck in just one location. You can go all around. Okay, so now to actually get into the main topic. So I'll kind of like skim over the why quantum computing and motivation side because Rohan already went deep into it. But just for some, just for completeness, like he said, classical bits are limited to these binary ones and zeros. But with quantum bits, we can span all combinations of ones and zeros where you have some linear combination denoted by your alpha and beta coefficients, where alpha and beta kind of, like I said, will denote the probability of your quantum state being in either 0 or in 1. So the picture is that classical bits are these like two nodes, 0 and 1, while quantum bits can span this entire circle of possibilities of combinations of zeros and ones. And the reason why the circle also spans into like coming out of the laptop screen axis is because the coefficients can also be complex numbers, which are like imaginary numbers. So your coefficients can actually span across that. And the reason we want to have that flexibility is that the phases of your different quantum states can overlap, and you need complex numbers to kind of denote that or to kind of explore that. Okay, so like I said, yeah, you can span all the combinations, but also how do we actually like physically understand what this is? It basically means that the probability of observing your qubit or quantum bit in any state, 0 or 1, is given by the coefficient squared. So the coefficient squared gives you the probability. So alpha squared will give you the probability of the state being in 0, and beta squared is the probability of it being in 1. And because probabilities always have to add to 1, we then have alpha squared plus beta squared equals to 1 as a normalization constraint. And kind of the reason I'm telling you this is kind of, yeah, just for completeness and knowing kind of what type of mathematical structure we're working with. Like over here, you see in the middle, there's a 0 plus 1 over root 2. And you have a square root of 2 in the denominator because when you square that, you get 1 over 2, which then gives us 50% chance of being in 0 or in 1 when you're in the middle of this circle. And so kind of what we're dealing with in quantum mechanics is that our states are vectors in some n-dimensional space. And one qubit is a vector in this kind of circular space with a complex axis. And this is analogous to the unit circle, which I'm sure you've like worked on like in maths and trigonometry, where the unit circle are just different vectors with all having distance 1. And that's why it's called a unit circle. And so a quantum state can be thought of as a point on the unit circle with its x-axis and y-axis denoting its probabilities of being in different states. Except you also have this coming out of this laptop screen axis denoting complex numbers. So that's some quick kind of mathematical basis just to have completeness. But what is the intuition here? Like, why is quantum computing important? Like, why is it like useful? Is because the intuition is that it can let us access an exponentially large number of states as we scale up our number of bits. So let's like look at it as just a tangible example with 4 qubits. Classically, you can only manipulate one bit string at a time. So maybe like 0110 is one example, or 1001. But in quantum, like quantum qubit, you can manipulate a superposition, which is a combination of all these bit strings at the same time. So all your states 0000 onwards to 1111 can be kind of operated on at the same time. And in the best case scenario, this gives us an exponential advantage because we can now manipulate all, so like for 4 qubits, it's 2 to the 4 states we're manipulating at the same time. And if we have n qubits, an arbitrary integer n, you can have 2 to the n qubits that you can manipulate. So in the best case, you have an exponential advantage in your computational time and process. So it's like a credit for 3 Blue, 1 Brown, the YouTube channel. So you should watch his video on Grover's algorithm. And this is the intuition he actually says not to use, but I actually think it is a good starting intuition to use until you get deeper into the algorithms. But the intuition really is, like I feel at the start, is that classically, you have this one thing, and quantum, you have all these basis states, as we call them. And then you basically keep doing operations on your quantum superposition until the probability of the right answer, so let's say we want x squared, the probability of being the right answer becomes large, and the probability of the wrong answers become small. And then we measure our quantum bit and get the right answer out. I feel like as a starting intuition, that is pretty fair. And yeah, I encourage you to go deeper into the algorithms to build your own intuition, as Rohan talked about. So yeah, Rohan talked about all these applications. I want to get to the physics now. So yeah, these are some applications of quantum computing. And yeah, those are all well available online. But like I said, physics is kind of what I'm most interested in this case. So where do the atoms come in for a quantum computer? So atoms are like, oh yeah, there's a teaser, as Rohan has said, we can have the so-called grid of atoms that we can treat as our computer. And this grid is actually from the Bernian lab at UChicago. We're actually moving out of UChicago now. But this is like a grid with two different atom species, cesium and, wait, sorry, I should know this. I think it's cesium and rubidium, but I might be slightly off. But yeah, but basically it's two different atom species that they can interact with. And these atoms can all act as qubits and interact with each other to form a computer. So how do we actually do this? So like I said, atoms are some of the most like fundamental quantum objects, and they're quantum because their energy levels are discrete. They're not a continuous spectrum. Everything in the world is like continuous when we like think about it in the macroscopic scale. Like if you're driving at 40 kilometers per hour, you can also drive at 40.00001 kilometers per hour, or anything in between. So it's a continuous spectrum. But for atoms, your electrons can only occupy discrete shells. And discrete means that there's only jumps in energy levels that they can have. And so this actually makes it quite easy to manipulate. Like it's because not easy to manipulate, but at least we can theorize how we could manipulate it. So let's say we can call a ground state where the electron is in the bottom shell, and an excited state, when we hit the atom with a photon, it jumps up to a higher shell, as you might have seen in like chemistry, that there are different shells. So we can now think about it as, so what is a normal bit? Like in the computer level, it's actually an electric pulse on is 1, electric pulse off is 0 for a classical bit. So we can actually encode information in some physical process. And now we can encode information, and let's say we can call the ground state the 0 state, and the excited state the 1 state. So we're basically constraining our atom to these two states. And then we're saying that when we measure our atom, depending on which state it's in, ground or excited, that means 0 or 1. So let's like look at a more complicated energy level. This is for the terbium atom. You don't need to like, this is just to demonstrate how there are a lot of different energy levels for atomic structures. And then the arrows are the different energies or light wavelengths required to manipulate the, to basically switch the atom from one state to the other state. So let's say we just focus on this green arrow. We can like look at the bottom state and call it 0, and then call the excited state from the green arrow the 1 state. So if we just use this green laser to just manipulate the quantum state of the atom between 0 and 1, we could think about it when the atom is constrained to only these two states, we can call that a qubit, only being in 0 or 1. Even though it has many other quantum states, as long as we can reliably constrain it to 2 states, we then have a quantum bit, being 0 or 1. So, but now like I've kind of glossed over the fact that it's not very easy to just trap atoms, like or have them in one place so that they can act as qubits and interact with each other. It's actually one of the hardest problems we have. Like the whole field of atomic, molecular, and optical physics has kind of led to a lot of tools that have gotten us to this point. And the whole picture of how to trap atoms is kind of long. So the teaser I'll give is how to slow down atoms. But if you're interested in the full picture, you can definitely reach out to me for more slides or materials. And if there's a mentorship program, then I'll probably go over that there as well and have some projects related to that if people are interested. But yeah, let's first talk about how to slow down atoms. So to slow down atoms, you require something called Doppler cooling. So okay, basically you might have heard about the Doppler effect in the past, where like in physics classes, but it basically is a fact that when any wave is coming towards something, or when you're moving towards a wave source, the wave will appear to have higher frequency. And when you're moving away from a wave source, the wave will have a lower frequency. And like everyone has probably experienced this in their day-to-day lives when, let's say, an ambulance with a siren or a police with a siren is coming towards you in the road, the sound will come like at a higher pitch. But as the police car zooms away from you, the sound will be at a lower pitch. And this is called like, this is the wave going higher or lower in frequency. And just like that, light can also, be shifted by the Doppler effect, where if you're moving towards the light source, its frequency becomes higher. And this is called blue shifted, because blue is a higher frequency. And if you move away from a light source, then the light will be red shifted, which means its frequency will be lowered. So, okay, why do we want to use this? So everything comes down to energy conservation. If you want to make an atom slow down, you want it to lose its kinetic energy. So what happens is you can basically imagine you have a light source. Okay, you have an atom's transition from 0 to 1, but you can send light at it at a lower frequency than this transition, meaning redshift, red detuned, which means that you're giving it less energy than it requires to go to the higher state. But okay, now the atom, if you just shoot it normally, this red light, it won't be excited to the 1 state because it doesn't have enough energy. There's this capital delta energy difference that doesn't let it get excited. But now you can imagine that if the atom is moving towards the light source, it will actually, there's animation here. Okay, it's moving towards the light source, and then it'll actually see the light as blue shifted. It will see the light as being at higher frequency than it really is in the lab frame, in our frame, which means that it will then actually get excited to the higher 1 state. But by energy conservation, that kind of doesn't make sense for us because we shot a lower energy light at it and it went to a higher state. So what this actually means is that in our frame, the atom must have given some of its kinetic energy to the process as well to go up to the 1 state. Or the other way to look at it is that it absorbs the momentum of the photon and it slows down. So it basically loses some of its velocity or momentum to get to the 1 state. It gives some of that energy, which slows it down. And so this is the process by which we can actually keep doing this, cycling the atom up and down in this process to keep, there's some nuance that I've skipped here for the interest of time, but the main intuition is this, that we can keep sending these red detuned lights at the atoms to keep slowing it down until we can get it to a level where we can trap it. So that's Doppler cooling. Then we can actually use this thing called atom tweezers. So these neutral atom systems are often called atom tweezer arrays as well, because the tweezer is kind of, you can imagine like pinching the atom and keeping it in place. And so the intuition here, I'll skip over the details of the math, but there's this basically potential well that gets created when you shine this high intensity light at an atom. And this potential well, if you make this delta negative, which is the detuning from the energy transition up and down, it creates a potential well that is negative, which means that it attracts the atom to the highest energy intensity point. So the only intuition I want you to get away from this without going into the full details is that you shoot this high intensity beam at the atom at some frequency, which is negatively detuned from the, basically at a lower energy than some transition of the atom from up and down, like from like 0 to 1. And then that keeps the atom in place as long as you keep that beam constant on the atom. And then you can use these things called spatial light modulators to transform one big beam into many dots, so like many like grid-like dot beams, to then trap a grid of atoms together. And like Rohan was saying, the great thing about neutral atom arrays is that you can move the atoms around. You can use things called acousto-optic deflectors that use sound waves to deflect the laser light beam left and right, up and down, to basically slowly, if you do it slowly enough, you can then keep the atom in your potential well and then move it along different directions. So big picture, we now have a laser array that traps atoms and we can move the atoms around. So we can imagine that now the atoms can interact with each other. We can move them closer together, move them further away, make them interact with each other, take them to different places to do measurements, computational readouts, quantum error correction protocols. We basically have a lot of flexibility using these atoms. So like Rohan was saying that I would try to like justify neutral atom arrays. And at this point, I feel like the physics of it is so fun that I don't even like feel like justifying for the quantum computing part. I feel like no matter what, neutral atoms will have some place in quantum technologies, and the physics is really fun. For justifying which is the one that will win in the future, time will tell. But my like guess is that all the different modalities will have some like tools we can use to make a working quantum computer. But I will talk about why scalability is very good with these atoms now, because basically we can build up these different atom arrays to create a quantum network where we can have multiple atom arrays working together to create a bigger effective quantum computer that can then scale up and do more computation. Okay, so I'll take some water there. So for quantum networks, first let me like motivate, I think I already alluded to it, but why do we need a network? So when we have this like experimental setup with an atom array, there's naturally limitations to how many atoms we can trap in one experimental setup. basically because of the microscope that we need to image the atoms with, they have some aperture, which means that they can only image some size of a space at a time. And the atoms also have to be spaced apart at appropriate lengths so that they don't start interfering with each other, and like basically the traps also not like collapsing on each other. So there's some limitation of how close the atoms can be together and a limitation of how much space we can image. So there's naturally going to be some technical limitation. Let's say even if we can trap 1,000 atoms, that's not enough to get a lot of like quantum advantage of. So we'll need multiple of these quantum computers together. And so if we have multiple quantum computers together, we need then a network connector, basically, that can transfer information from one array to another. So fundamental issue we have here of quantum mechanics is a no cloning theorem. So to illustrate this, like, what does no cloning mean? Classical bits can simply be copied from one computer to another. So if you have computer 1 with some bit string, computer 2 is initialized to have a 0 bit string. We then use network transfer device, let's say, an arbitrary device, to then transfer from this computer 1 to computer 2 our bit string. Okay, like normal network. But in quantum mechanics, there's a no cloning theorem that prevents this. So say we have some quantum state, denoted as psi, and some initialized state in another quantum computer, 0. If we have some quantum network transfer device, you can transfer the psi state to quantum computer 2, but in quantum computer 1, the qubit will be destroyed. The information will be destroyed. And this is a fundamental fact of reality, that an arbitrary quantum state cannot be cloned. It can only be teleported. Speaking of teleported, so physicists like saw this as this was a problem, but then now we can just give it a fancy name. We can just call it teleportation, where we're teleporting our state from one place to another. So this does limit the types of computations and algorithms one can do with multiple quantum computers in a network. But it turns out that even with teleportation, you can scale up a lot of a big modular quantum computer from small pieces. So it isn't the biggest issue. But to actually know how to teleport a quantum state, a quick aside, I need to talk about quantum entanglement, which I think I would like you to get out of this anyways, because that's like a fundamental thing of quantum mechanics. So one qubit can be in a superposition, as I said, of the 0 and 1 state. But what if you have 2 qubit states that are prepared in the following superposition? So this is a joint qubit state now, where it describes qubit 1 and qubit 2. If you have a 0, 0 plus 1, 1 state, this basically means that qubit 1 is 0 and qubit 2 is 0, or qubit 1 is 1 and qubit 2 is 1. So this is still a superposition where there's a 50-50 chance of one qubit being 0 or 1. But the crazy thing about this type of state, which we can prepare, is that we don't know the exact state of our qubits before measuring, but measuring one qubit immediately tells us the state of the other qubit. If we measure the left qubit and find out whether it's in 0 or 1, we immediately know that the right qubit is in 0 or 1, depending on our measurement outcome. And no matter how far apart you put these qubits, this information is immediately transferred. And so this is what Einstein called spooky action at a distance, because he thought it was like scary or like really bad because it violates information being transferred faster than the speed of light. But actually, if you go into the actual mechanics of this, information is not transferred at the speed of light, because normally to do an entangled measurement, you need to have some classical communication, which follows the speed of light rule. But it is true that the so-called like the universe is kind of telling that one qubit somehow transfers the information to the other qubit immediately, instantaneously, that it has been measured. And this is a true thing that has been tested. So it violates something called locality, which means that the two things don't have to be in the same vicinity within the speed of light time to communicate some information, even though this is not useful information for us. But basically, yeah, an entangled state is our resource for quantum teleportation, because what we will do is we will have an atom 1. Let's check how much time. I'll speed up slightly. So atom 1 will be in our quantum state psi, but on the other side, we'll have an entangled atom photon pair, the same entangled state I was talking about, where both are 0 or both are 1, but in a superposition. And what we will do is we will send our photon from atom 2 to atom 1, and we will do something called an entangling operation there, where we entangle atom 1 and the photon in a way where we can transfer classical information to then project atom 2 onto our quantum state of atom 1. So the intuition here, there's a lot of mathematical details that I've skipped over, obviously, and I can give readings for that as well if people are interested. But the intuition is that the entangled state of atom 2 and the photon has been transferred to atom 1 and photon, and has swapped the quantum state of atom 1 to atom 2. So we've kind of done an entanglement swap. And to the magic of entanglement, we've now teleported the quantum state from atom 1 to atom 2. So this is how a building block for a network could be built, where in different atom arrays, we then transfer information between each other to do scalable computation. And the last piece of the puzzle here that I'll talk about is how do we actually entangle an atom and a photon? So this is actually using this thing called optical cavities. So the lab I'm working at Harvard is called the Lucan group. It does a lot of different experiments. My subgroup is called the atom cavity group because we're actually focused on really like linking these atom arrays quantum computers to optical cavities to build up to a quantum network. So these cavities actually help us by enhancing atom photon interactions. So optical cavities are these like kind of two joint mirrors at different ends. And you might have seen in the physics classes where if you have a standing wave, you can basically have constructive interference with a standing wave where you build up a wave with two different edges, as long as the wavelength of the wave is the same length as your kind of box. So basically what happens is you have two mirrors at each end, and you keep shooting photons or light at the resonant frequency of the cavity into the cavity. And as the photons come in, they bounce back and forth, adding, like all adding together to build up a very strong field. And this field can then interact with our atom very well because we place an atom into the cavity, and this basically creates a resonant field interaction that enhances the light matter interaction. So what this actually means for us is that we can then have a higher rate of atom photon interactions than in free space, which is without a cavity. And we can then use this to have very quick atom photon entangling operations and interactions. And how do we actually entangle this thing? This is actually the last part. Yeah, I think I'm good on time. Yeah, so you use the cavity enhancement to excite the atom from the ground state to the excited state, which I talked about previously, like the 0 and 1, at a high rate. So light comes in, your atom get excited to the higher state. So now I obviously have to omit a lot of quantum mechanics things, but one thing to take for granted is that adjacent to the ground state, there are these so-called states called spin up and spin down states. And if we let the atom kind of go down by itself, it will go down to either the spin down or the spin up state. And the spin down and spin up can be thought of an angular momentum shift, where you've gone from 0 angular momentum to down angular momentum or up angular momentum. But because of conservation of angular momentum, it will then shoot a photon that is either right circularly polarized or left circularly polarized. And if you've ever seen like circularly polarized light, in this case, it's basically a photon of left or right circularly polarized, which is a type of polarization, encodes like an angular momentum direction. So because of conservation of angular momentum, based on whether the electron goes down to the down state or the up state, the photon emitted will be left polarized or right polarized. But there's a 50-50 chance of the electron going down to either spin down or spin up. So then you basically produced an entangled state, because now you will either have electron down and photon right, or electron up and photon left. This is the exact same thing as entangled state I was talking about, because you can just replace your arrows and the right and left with a 1 and 0 to recover the entangled state, 0, 0, and 1, 1. So using this process, you've now basically got an atom photon entangling scheme that you can now use to build your network. So yeah, last part, rushing slightly, but I hope that part was clear enough, that now the big picture will be that we can then have network connectors that are pairs of optical cavities that transfer entanglement between atom arrays using photons, where the atom talk to each other using photons that are entangling them. And so you now can build up higher and higher with more atom arrays and more cavities to build up a so-called modular quantum computer, which can scale up indefinitely as long as you can have high enough rates of entanglement and quantum network operations. So more qubits will equal more access to more quantum advantage. And yeah, so this is the big picture of what we're working towards. So yeah, I'll take any questions, but just to have something tangible as well, this is my work from last summer at Harvard, where I was in one of the labs building a vacuum chamber. The vacuum chamber is where the atoms are housed. So when we were building the vacuum chamber, you had to wear this like clean suit, which is like a full-on like protection suit, so that you don't contaminate the inside of the vacuum chamber with oil or hair or anything. But once you build a vacuum chamber and the vacuum is there, then you can it's fully built, then you can wear normal clothes, come in normally. And this is a picture of us shooting lasers into the vacuum chamber, where the atoms will be in this glass cell. So the atoms are actually trapped in there. But you need this whole process to get the atoms there and slow them down and trap them. So yeah, I'll stop there and take questions. Yeah, I hope you all enjoyed. Thank you.
Thank you very much for that talk. That was awesome. And I wanted to forward to you one question that was sent earlier in the chat, which apparently just disappeared. But a question that was sent is that what's actually the hardest part of scaling up the neutral atoms Q computers? Is it more about controlling the lasers, keeping the atoms in place, or something else? The person asking the question have also read about Majorana particles, which are their own antiparticle, and they've read that there isn't really a way to harvest them due to their high energy rarity. Do you see an application for them in the future?
Yeah, so for the neutral atom side, so scalability, like I said, like just like normal microscope objectives have a limit to how much space they can reliably like image at one point, how much they can focus on. So you can try to build an atom array that can go with bigger and bigger microscope objectives, but there's like a limit to that, and also because of how much the atoms can like be spaced from each other. And you also want to create like a homogeneous imaging system where like if the sides of like a microscope objective will actually start to kind of skew the image a bit with the parallax errors, you want like the atoms to be like centered to a microscope objective to have the most like reliable images, because you should image the atoms to get this quantum state out. That is the measurement, and that's the part that you need to be the most reliable for computation. So that is one thing. I think the limitation, basically, like once we actually get these quantum networks working with like really reliable high entangling rates of information transfer, like one can imagine that maybe there won't be like a like proper limitation to how much we can scale up. It'll just be based on like time and resources of like making more of these atom array kind of equipments. Once we crack like the like network interludes, actually scalability will be pretty good, but that's still a big if, and that's still something we're working on. Yeah, and on the Majorana fermions, I don't actually know too much about it. Like the actual physics of it is pretty advanced with like a very deep condensed matter and topological physics. So like topological quantum computing, if it can work, it'd be very cool because it'd be like physically it would be quantum error correcting itself at all times, because just the topology of the way the qubits are like arranged or the particles are arranged would become a so-called quasi-particle that can then correct itself and keep it like its information safe. So that's a very cool idea. Like Microsoft has been trying for I think like 2 decades, and they haven't gotten to do it yet. But they're like really smart people and they're trying, and I think more people should try. But so far it's looking a bit tough. But I would be very happy if we can get topological qubits to work.
Wonderful. Let's just wait and see if anybody has any other questions. If you do, feel free to leave them in the Q&A section or in the chat, depending on whichever streaming service you're currently using.
Also, if you'd like to ask a question verbally and raise your hand, please do so.
Exactly.
I think there is a question among the answered ones, maybe anonymous. How many qubits would you actually need to solve an interesting problem? The few ones we haven't answered it yet, right?
Yeah, so I think Shor's algorithm requires like something about on the scale of you need how many qubits, like proportional to the number of bits in the integer that you're factoring, which is like the prime number. So I would, let's say like okay, let's say like a 2048 bit RSA number, you would need like in the scale of like millions of physical qubits, if I'm not wrong. I might be actually wrong there. But basically, yeah, you need some large amount of qubits. And the issue is also that our current, okay, sorry, I meant physical qubits. And physical qubits, because you need multiple physical qubits, just like multiple atoms to kind of form one logical qubit, where the atoms actually all correct each other, as Rohan was alluding to with quantum error correction. So multiple physical qubits that can error correct for each other will then form one logical qubit. So you need on the scale, yeah, for physical qubits on the scale of maybe like a million, yeah. Which is why we need scalability really badly.
Yeah, sorry to
Thank you so
jump
much.
in
Oh, yeah.
here,
Yeah,
but
Rohan.
but the answer to this question is exactly as Shivam said, like almost exactly a
Okay.
million. There's this new paper. His name is Craig Gidney from Google. You can search it up, but it was big news about 2 weeks ago in the quantum computing community. He basically found a way to reduce the number of physical qubits you need from about 10 million to 1 million, which is pretty good. So
That's solid. Yeah.
oh, but sorry, and just one more thing, not to take this over, but like that's only for Shor's algorithm, and Shor's algorithm is probably one of the most demanding things that we can possibly run. You probably need maybe on the order of like a few 100,000 for like things like chemical simulation to start to be interesting.
I've got a personal question. I'd like to ask about the scalability of this. Having less qubits, would having, for example, half the qubits mean you can just run them for twice as long, or does that not really apply to quantum computers?
Yeah, Rohan can answer this again afterwards, but like from what I understand, there's some like critical mass of multiple qubits so-called interacting with each other at once, or like kind of interfering with each other to get the required number of like basically often when you have the algorithms, they'll have some error threshold of kind of how off they are from the true answer. And as you scale up the number of qubits, that error threshold gets smaller and smaller. So often for an acceptable threshold of error, you need some amount of qubits. So like you can't like overcome that error threshold by spending more time. That's like a fundamental limit. You need the number of qubits you need.
Right, and just
Right,
to
thank you
add,
so
like if you run something for twice the number of times, you're also exposing yourself to twice the number of errors. Like this is
Right,
the general intuition from classical computing that you can just use less resources for longer time is a little bit tricky here, because again, the stack is doing two things. It's trying to suppress errors and it's trying to do the abstraction thing. And the errors will scale with the amount of time that you're spending doing the computation.
Understood. Thank you so much.
We also had another question about how big of a space a fridge would take, and how big the whole system would have to be in that case.
Yeah, so for neutral atoms, actually we don't use fridges like I showed in that picture at the end. We use like these vacuum chambers. So, but people use fridges for superconducting qubits because you need like your chip to go down to those like 30 millikelvin, 70 millikelvin temperatures, very close to zero energy, to have its like resolvable quantum states. Because as soon as you get to higher temperatures, the quantum states all get blurry and mixed. But for atoms, yeah. So the fridge for superconducting qubits will probably take like I don't know, like the whole system with all the electronics and stuff. Maybe like I don't know, a standard classroom, or like a quarter of it, or maybe like a fifth of it, the space. And I actually, if I share my pic, let me see. Can you see my slides again? Basically, like for the atom array, you basically require. Yeah, I don't know if you can see my slides yet, but you require twice the size of this like half room, because you need a whole table. Your lasers need to be so well stabilized, and so like the frequencies that address the transition of an atomic transition, they need to be so stable to reduce noise and to reduce anything to like let you have useful computation. And you need a whole optical table just for laser stabilization and different techniques to like make the lasers better. And then you have a whole table where your vacuum chamber is, where the atoms are trapped in the vacuum, and you can then shoot your lasers into the atom array. So right now, yeah, people do require space. Like you require a whole lab space or a half lab space for one quantum computer. And this issue is not looking to, yeah, space is not something that is solvable for a while until we get miniaturized components. But the future of quantum computers is more like a supercomputer that you can have at some source, and then you can kind of send in queries from the cloud into the quantum computer. So yeah, you're not meant to be looking at having your own personal quantum computer anytime soon. Yeah.
Maybe a quick question from me. Sorry, excuse. Maybe a quick question from me as well, if we're not too short on time. I was wondering also, maybe since you're talking about having your own quantum computer, I was just wondering about, hybrid classical and quantum computers and their possible applications, like in general, because there's a lot of discussions happening about where classical and quantum tend to like converge at a certain point, and where we can use a mix of both, at least for now, until quantum computers are efficient with the qubits. So like right now, if we were to use a hybrid model, what could we get done?
Right. It's also probably something that Rohan can add after. But from what I understand, that let's say like in some of the new Google papers from last year, they're actually using like so-called like machine learning algorithms or reinforcement learning algorithms to the classical side can basically take some output from the quantum side of, let's say, like some noise model or what is happening to the quantum computer, and then it can go through some classical optimization algorithm to then change the parameters of how you're controlling your quantum system to reduce the noise and to basically get better information out of it. So you can have a quantum classical kind of repeater loop where the quantum side outputs something, the classical side takes it, analyzes it, and then changes the control parameters of your quantum computer to then kind of converge towards better data or like less noisy qubit. That's one application I know of for classical quantum. Yeah, I think, I'm not sure, Rohan might have.
Yeah, I guess like I mean that's the hardware side of it, like using classical quantum hybrid stuff to just make quantum computing better. The other thing is that like there are just like straight up algorithms that you need like sort of computational feedback from a classical computer from. One like set of examples, you can search this up. I mean, this is a long thing to like sort of explain in a brief Q&A, but like the class of algorithms is called variational quantum algorithms. Some examples are like the quantum approximate optimization algorithm or variational quantum eigensolver. The idea is that like you let the quantum computer do the hard part of like whatever algorithm you're doing, which in this case, for example, for molecular simulation, is let's say calculating the energy of some parameter of the molecule. And then you basically feed that energy back into the classical computer, and you basically run gradient descent on like some parameters that you feed back into your quantum computer to basically converge upon like what the ground state energy of the molecule would be. Like this is just one example. But you know, there's this feedback between, you need to have very, very tight control electronics to be able to like feed back information to the quantum computer to be able to actually do all of this well. So it's an algorithms problem, it's a hardware problem. It's very interesting. You know, they have pros and cons, and a lot of like labs have like their own different takes on whether classical quantum hybrid algorithms will ever actually show advantage. I'm optimistic because I think that when quantum devices get up to scale, we'll be able to actually experiment with them rather than just like writing mathematical proofs as to like why certain things are good and bad. So I guess that's like my take.
Thank you very much for both of you for well, the great talks and also answering the questions. With that, I'm gonna get ready to introduce our next speaker, Attila Kovacs. Attila graduated from UWC Adriatic in 1993 and is now a far-infrared sub-millimeter astrophysicist, currently working at the Center for Astrophysics, Harvard-Smithsonian. He does a mixture of observational and computational science, new detector technologies, instrumentation, and telescope control systems. A fun fact about Attila is that his main hobby is cooking and eating food from all around the world. Attila Kovacs will now teach us more about far-infrared astronomy from the ground, air, and space. Thank you.
Thank you so much for the introduction, and thank you for the organizers for making this amazing event, and thank you for all those who tuned in from all different time zones. I assume for some of you it's morning, for some of you it's night. So good morning, good night, good evening, good day. Yeah, so I'm going to give you just a very brief, like bird's eye overview of what far infrared astronomy is. And of course, I cannot cover everything. In fact, I feel like I have to leave out more than I can actually cover, but I'll try to do the best to at least give you a flavor of it. So here on the starting slide is actually like, just for curiosity, is two panoramas from Mauna Kea in Hawaii, which is actually some of the first sub-millimeter telescopes were. So on the top one, you see this little golf ball on the left side. That was the Caltech sub-millimeter observatory. That was the telescope where I basically got trained on. Unfortunately, it's no longer there. So it has been removed last year. Next to it, the big one in the foreground is the JCMT, which is the largest sub-millimeter telescope for a while. And then on the bottom is those 8 antennas is the sub-millimeter array, which is the telescope I currently work with. So it's switching a bit gears here to astronomy, so I'm going to give you a short introduction of what far infrared astronomy is. And then I'm going to cover basically some of the main topics of sub-millimeter astronomy or far infrared astronomy. So which are star formation. That's probably the biggest question that we try to address. There's astrochemistry. I talk a little bit about planet formation and about galaxy clusters. So that's really basically all all there is. So let's jump in. What is far infrared? So of course we are all familiar with visible light, but the electromagnetic spectrum is very, very broad. So light can come in all different flavors, and this is basically all the way from radio waves, which are at the long wavelength, gamma rays on the short wavelength. And visible light is this very, very relatively narrow band in this full broad spectrum that is available to us to study the universe. So next to the visible is, of course, we are biased for visible light because we are sitting next to a star, the sun, which is blasting us with visible light, and now that basically blinds us to everything else. But we shouldn't be so biased. So short of visible light is various infrared bands. So like first it's near infrared, then it's mid infrared, and then comes far infrared. So far infrared traditionally is defined as basically anything between 30 microns to 100 microns in wavelength. And then there is submillimeter, which is basically from 100 microns to 1 millimeter, and then millimeter is millimeter wavelengths, which is typically 1 to 3 millimeters. But in some sense, this separation of millimeter, submillimeter, and far infrared is a little bit artificial. It was done historically like that because of technologies. So we use different technologies at these different wavelengths, but we actually really study the same thing. So I like to call all three of them as far infrared, just to make it easier to refer to it. And what do you see there? So typically what you see is cool radiation from things that are, somewhere between a few Kelvin to 100 Kelvin in temperature. So, okay, what does the universe think about that? Is that interesting in the universe? So this is basically a plot of the, what is the distribution of photon energies in the universe? So what you see here is on the x-axis is frequency, and on the y-axis is a logarithmic scale of how much energy is in the photons carried at those frequencies. So right away, what you see is that the biggest thing here is the CMB, which is the cosmic microwave background. And then next to it is the cosmic infrared background, then the optical background, and then it's the X-ray background. So right away, you see that, and then I basically show the blue shaded area shows where the optical band is, whereas the orange one shows where the far infrared bands are. So right away, you see that there is a lot of light. So actually, the dominant part of the energy of photons in the universe actually comes in these far infrared bands. And of course, I'm cheating a little bit because if you look at the CMB, most of the CMB is extremely uniform. It's uniform to the 1 part in a million. So there's not a lot of structure there. So it's not really telling you about where galaxies are or anything. If you remove if you are looking at the structure in the CMB, then it becomes that green curve below. So if you are looking at structure in the universe, then it's even that it's even more stands out that this cosmic infrared background is basically the next brightest peak. So most of the structure in the universe is radiating at wavelengths. And that's actually, I think, some of the, if there's something that you should take away from this talk today is that. So the universe makes it interesting. So why don't we all do far infrared astrophysics? And the answer to that one is because it's hard. It is very hard. And especially from the ground, it's very difficult because we have an atmosphere which is not very transparent at these wavelengths. So this plot on the left side is basically an atmospheric transmission plot from, basically, very low frequencies like radio wavelengths all the way up to 2 terahertz. So that's basically most of the millimeter and submillimeter bands. And this transmission plot is done for one of the best sites at high altitude. So it's at 5,600 meters in Chile. And for different weather conditions. And only in the very, very, very best weather do you get actually the transmission in the millimeter, submillimeter bands that is kind of decent. So it is hard. So because of that, we want to go high, as high up as possible. So there's some of the instruments here are the 30-meter telescope in Spain. It's around 3,000 meters, and it really only works at the millimeter band. And then if you want to go into the higher frequencies, into the sub-millimeter, then you have to go higher. So we have the SMA, the sub-millimeter array, the one I work at. It's in Hawaii at 4,000 meters. Or you have ALMA, which is even higher in Chile at 5,300 meters. And if you want to go even higher than that, then you have to become airborne. So there was this airplane telescope, SOFIA, that was operated by NASA. So it was flying around 13,000 meters or 45,000 feet. If you want to go even higher than that, then you use balloons. So there's a bunch of that run on balloons. So an example is BLAST, Blast from the Past. Beyond that, you have to go into space. So this is one of the, this makes it a little bit difficult. The second part is that, because you are at longer wavelengths than optical light, that also means that you are suffering for resolution. So if you're using a small telescope, it's going to give you a very blurry image. So you need large telescopes. So, you can either have single dish telescopes like the IRAM 30-meter, or there's a 50-meter telescope, the LMT, the large millimeter telescope in Mexico. And there, Europe is actually thinking of building a 50-meter sub-millimeter telescope in Chile, which is also 50 meters. That's about as big as you can do on a single dish. So the other possibility is that you do interferometry, where you actually combine radiation from multiple antennas, and you make them work like as if it was one large aperture. So, the largest telescope we have currently, as such, is ALMA in Chile. So you typically have, baselines of up to a couple of kilometers. So it basically works as if it was a single telescope of a couple of kilometers in size. And there is an even larger one, which is the Event Horizon Telescope, where you actually use multiple facilities from around the world. So you're basically using the entire globe as your aperture. And so the EHT, of course, is famous for making these images of the donuts, which are the black holes of M87 and the Milky Way. And these are the highest resolution images ever produced in astronomy. They look like blurry to you, but they are basically produced at a 19 micro arcsecond resolution. It's mind-blowing. So it's basically, it's more than 1 million times finer resolution than what your eye can possibly see, even with a regular optical telescope. So the third problem, the third challenge that we have, which makes sub-millimeter or far infrared difficult, is that there's no commercial technologies. So we actually kind of have to innovate and make our own detectors to be able to do this kind of astronomy. And so it's actually kind of interesting that we had this, quantum computing talks before, because actually some of the devices, the superconducting devices that they use in quantum computing actually came out of sub-millimeter astrophysics. So these are typically these superconducting junctions that I think usually used as a Josephson Josephson junction. But we basically make different kind of detectors. So they are all, none of this is commercially available. And so we kind of have to go into the lab, and we typically use thin film lithography to make devices. And then you cool them down, typically to something like 60 to 300 millikelvin, or some of the devices can actually live at a higher temperature of 4 Kelvin. And then you need a large cryostat. And so, sorry about that. On the right, you can see that that's basically Scuba 2. That's one of the cameras which has 10,000 pixels, and you need a very large cryostat for that one. So basically this big box is just to ensure that you can cool down your detectors to the operating temperature. One of the other problems that we have is that it's very difficult for us to read out a large number of pixels on a single wire. So if you think of your digital camera typically, then you have a megapixel camera, and all those pixels are basically read out on a single readout line. For us, it's very, very difficult. So the most we can do is maybe put together 1,000 pixels per readout line. So already when you have 10,000 pixels, that means running 10 wires from this 60 millikelvin or 300 millikelvin stage out into the room temperature environment. And that becomes very difficult. So what do we look at when we look at in submillimeter astrophysics? So, it depends on basically anything in any era of the universe, all the way from the cosmic microwave background, which is basically the earliest light that we see from the universe. So then the top part is kind of like a, it's a graphics that is indicating what the history of the universe looks like. So on the left, we have this cosmic microwave background, which is basically the time when the universe has become neutral. And after that, the universe was dark for a couple of million years before the first stars and the galaxies started to form, and and then more and more structure forms over time, and then we arrive to the present day. So in the far infrared, you can see stuff from all across that. So you can see the cosmic microwave background, and you can see the structure and the polarization. You can see galaxy clusters. You can see star-forming galaxies. You can see accretion, such as active galactic nuclei or tidal disruption events. I'm not going to talk about those today, but feel free to ask me questions about them if you are interested. There's also within the galaxy, we can look at star formation inside of our galaxy and look at star-forming regions up close. We can look at planet formation. So we can look at, how when after stars form, how do the planets form around the star from the disk of dust. In general, we can look at dust and dust, the properties of distribution of interstellar dust. And finally, we also look at molecules. So it turns out that basically most of the interesting molecules in space, other than hydrogen, they have typically rotational transitions in the far infrared bands, millimeter and submillimeter. Okay. So back to this picture again. Let's talk about star formation. So what is this light that we see in the far infrared at these temperatures of something like tens of kelvins or 10 to 100 Kelvin? But it turns out that it's basically also starlight. So, but it is starlight that is reprocessed. So if you look at star formation, which is literally inset, you look on the right. So stars form in a very dusty environment, which means that that their light is basically absorbed, and it doesn't arrive to us directly. So when stars form, we actually don't typically directly see them. The dust has to clear before we are able to see the star. So, and while it's enshrouded by the dust that absorbs the light, it heats up the dust and then it re-radiates it as this cool thermal radiation. Okay, dust is very similar to the way you think of dust. So it's really particles of usually silicates or carbonaceous materials, basically the building blocks of what Earth or the other planets or asteroids are made of. And this is how it's related to star formation. So you have that gas that collapses, and it turns out you can't collapse gas to form a star without having some dust in there already. And in fact, we do not know how we form the first stars without dust. The dust is necessary because radiate very efficiently energy away. And when you're collapsing materials to form a star, you have to get rid of a lot of gravitational energy. Otherwise, the collapse will basically stop. So dust plays an important role to form stars, and then it's basically enshrouding the stars. So like when the stars were formed, they irradiate this dust, and when the stars die, either as supernovae or form planetary nebulae, they basically produce dust and they release it back into the environment. Okay. And while they are, the most of the dust is heated by the most energetic stars, which are also the most short-lived stars. So these are stars that typically live for only about a million years or less. And so in that sense, when we are studying the dust and we are looking at its luminosity and temperature, we really are getting a snapshot of what is the current star formational rates, sort of averaged over a million years. So if you look at, this is a views of the galactic center. So looking at towards the center of the Milky Way, and the bottom is the optical view. And so what you see in the, this is what you are used to. You are seeing a lot of stars. There's the Milky Way when you look up at the sky. But at the center of the Milky Way, there's this dark bands. And in fact, if you go out into the night sky, if you have a nice clear night, you can actually see that band with your bare eyes. So the Milky Way splits into two, and there's a top and the bottom part, and in between there is darkness. So we don't really see much towards the center of the Milky Way. But then if you go to longer and longer wavelengths, the dust becomes less and less inhibiting, and you're starting to see actually the star forming gas is starting to light up. And the top, that's basically a millimeter wave image of the galactic center. And what you see is that basically the stars completely disappear. We do not see any stars, but all the star forming gas lights up. And so what is bright here is basically all the star forming regions in the galaxy. And you can see that, the galactic center itself is extremely bright. There's a lot of star formation that is happening there. In fact, that's basically where most of the stars of our galaxy currently form. So it's a very different view. Let me see if I can. Why is my thing not working? Oh, there we go. Of course, you can look at star forming regions also nearby. So this is, this is from the Hawk Plus camera from Sophia that I also worked on at some point. So this is the Orion molecular cloud, which is basically it's the closest star forming region to us. And because of that, we of course studied a lot. So the three images on the right are taken at different wavelengths, 50 microns, 90 microns, and 150 microns. And you can see that the structure changes already in those images. The left side, which is, I think, not such a clear picture, is kind of a composite. It's just a view of how the different wavelengths are superimposed on each other. And you can see it has a quite complex structure. And certain wavelengths you see filaments, filamentary structures, and other wavelengths you don't. So you see, hotter or cooler dust, basically. Another way to look at dust is you can also look at polarization. And it's because those grains of dust are typically not very spherical. So they have, they're a little bit, oblate in some direction. And it turns out when you have dust that is not symmetric and it's spinning, then it tends to align with the magnetic fields over, something like, I think, thousands or tens of thousands years of time scale. But because of that, because it aligns with the magnetic field, it will, and it has an elongated shape, that affects the polarization of the light that it emits. So we can measure that polarization. It's typically, on the level of like 1%. And that polarization basically traces out the magnetic field in the plane of the sky. So this is a star forming region, and the color is basically the intensity of the far infrared light, and then the arrows, or not arrows, the little bars, they show basically the direction of the magnetic field around that. And this is important because we know that play an extremely important role in regulating star formation. So we can also look far away. We don't have to look into our galaxy, and we can look at star-forming galaxies. So at the bottom is a couple of different galaxies. So there's elliptical galaxies that they are old and dead galaxies. They basically contain light from old stars, and there's basically no star formation going on. Then you can have galaxies like the Milky Way, spiral galaxies, and these galaxies tend to have a lot of dust. And they produce stars at some rate, produces about 1 star every year. Then you can have starburst galaxies like NGC 253. So these are galaxies that have a higher rate of star formation, something like like 100 stars per year. And finally, you can have ultraluminous infrared galaxies like ARC 220, which produce something like 1,000 stars per year. So one of the interesting facts is if you look at it, so the Milky Way has about 100 billion stars, and it's forming, one star a year. So clearly, the universe is only about 15 billion years old. It had to, in the past, form stars at a much, much, much higher rate than what it does today, like orders of magnitude higher. So these starburst galaxies are kind of a template of what the Milky Way may have been, something, 5, 10 billion years ago. Energy distribution from these galaxies. So that's plotted on above. Again, you see that for the star-forming galaxies, so that those are the kind of the bluish ones. The far infrared or submillimeter is basically the same bright as the optical. And then for up to R220, which is the highest star-forming galaxy, it's about 100 times brighter. So for R220, so it's kind of a funny thing. It looks this wimpy thing in the optical. It's actually the brightest galaxy in but something like 99% of the light does not come out in the optical. It comes out in the infrared. So this is interesting. One peculiar quirk of nature here is that galaxies don't get fainter in the far infrared when you go to larger distances. It's a little bit counterintuitive. But basically what happens is that you have this spectral energy distribution, which is, you can see it on the left. And as you look further, it becomes dimmer, but it's also shifting to the longer wavelengths. So at the end of the day, basically, if you are observing around 1 millimeter, the brightness doesn't really change much. And so this is basically on the right, you can see how bright a galaxy would appear, being close to us to the edge of the universe. And you can see that green curve, which is 1.2 millimeters, is basically flat, which tells you that, you can observe a star-forming galaxy the same, whether it's next to us, next door, or if it's at the edge of the universe, which is an amazing thing, because that means we can actually conduct really unbiased surveys of star formation in the universe. Okay, I'm a little bit low on time, so I'm going to speed up a little bit. So the other thing you can do is you can look at molecules. So of course, the most common molecule in space is hydrogen. And hydrogen comes in different forms. It can be ionized, it can be atomic, or it can be molecular. Molecular is the most interesting one for star formation because the molecular hydrogen is what traces the dense cold material in which stars form. But we cannot actually see it directly. So we either use dust as a tracer of it, or we use carbon monoxide. And maybe one interesting fact to point out is that actually we can also not form molecular hydrogen by itself. So like, you would think that you have atomic hydrogen in space and they just meet and they become molecular. That actually cannot happen, it turns out, not in the gas space. So they need actually the surface of dust grains so that you can take atomic hydrogen and convert it into molecular hydrogen. And I think that's another interesting fact to take away. So rather than looking at these continuum images, you can also look at spectra. So on the left is basically like a broadband spectrum, and you can see a lot of lines, and you can see there are labels, so there's a lot of molecules. But even at the bottom, which looks like the noise, I'm zooming in at this purple shaded area that's shown on the right. Even that is basically, it's not noise. You are seeing lines everywhere. So there's like a gazillion species of molecules that we can see at these wavelengths. And some of them are very weird molecules. So the left is basically carbon chain molecules that, they're extremely unusual for chemistry on Earth. So you can have, for example, up there's 17 carbons with one hydrogen on one end and one nitrogen on the other end. So, it's a molecule that would never exist on Earth. But in space, the rules of chemistry are a little bit different. So we have these strange kind of molecules, and you have a very restrictive network of interactions that can happen. So that picture on the right basically shows such a chemical network. What these molecules on the spectra allow us is basically we can study the physical environments of the interstellar material in many, many ways. So we can get temperature, mass, velocity. We can study shocks and turbulence and chemical networks and redshift, name it. So basically, this is our main diagnostic of how we learn about the interstellar medium. I'm going to skip this one. If you want to ask me about it later, go ahead. It's basically, planet formation is another hot topic these days, and it's again also happens in the far infrared and submillimeter. I'm currently involved in a balloon mission that is hopefully going to launch in 2018, unless Donald Trump decides to cut our funding. We'll see about that. It is to study basically planetary disk and figure out, learn a little bit about how planets are forming. Another thing you can do, and I think I'm going to try to wrap up, is to study, moving away a little bit from dust, is to look at clusters. And here we use something cool, which is called the Sunyaev-Zeldovich effect. So I mentioned you that most of the light of the universe is this cosmic microwave background. It basically lights up the entire universe, and it's very uniform. So, but as light comes from this very, it's at the very edge of the universe that we know. So as light comes towards us, sometimes it travels through material. And if this material tends to be dense and hot, it's going to basically change that light. So it's going to basically scatter photons from low frequencies to higher frequencies. And it's going to change the shape of this curve. And so what you see on the left is that basically the original was the dashed line, and then you're scattering it into this other line. And at the lower frequencies, around 150 gigahertz, you have a decrement compared to the original light, and at the higher frequency, you have an increment. And that's what you see on the other side. So you can look at this in the submillimeter as well. It's again, it happens right around the 1 millimeter. So this is an example of a camera. This is the Gizmo camera at the 30-meter telescope. And this is what a cluster looks like with Gizmo. And it was interesting because most of the SZ clusters before were detected by instruments that don't really resolve structure, spatial structure. So they are just blobs. And it was kind of assumed that all these clusters are very, very nicely thermalized and they are settled. But it turns out there's actually a lot of structure in them, some of them, and it's probably a result of recent interactions. So let me wrap up. So this is my conclusions. I think the universe thinks that far infrared is actually kind of a cool place to be, even if we don't think so ourselves sometimes. The main topics are star formation, structure formation, anywhere from planet size to clusters, astrochemistry, and it's all tied in with new technologies because we need to create our own detectors to be able to study these things. And this is my closing slide. It basically shows how many astronomers are in the different fields per wavelengths, and you can see that most astronomers work on optical or X-ray or high energy astrophysics. There's very few of us in the far infrared and submillimeter, and I hope that's going to change. So we need bright people like you to join the field and make a difference. So thank you. That's all.
Thank you again, Attila. That was a wonderful talk. It's awesome to learn about far infrared astronomy. And we already have questions for you that people have been sending in the chat. One that I wanted to forward to you comes from Alex Diamond-Stanek. What do you think about the future of far infrared astronomy now that we don't have telescopes like SOFIA, and the future of telescopes on sites like Mauna Kea is unclear?
So that is a good question. So there definitely has been like a divestment from the field. As I said, it's difficult. So it does require a fair bit of investment. NASA does not have a flagship mission in the far infrared right now. The last one was Herschel, and there's nothing planned for the next, at least decade. Some of the single dish telescopes are aging and they are getting decommissioned. But despite of that, I'm kind of optimistic. I think there's new ones coming online. So ALMA is going strong, and this telescope is like At Last, which is being planned. So and there is, balloon mission. So I think, yes, the airplane, Sophia is not flying again, or anymore, but in many ways, balloons can do as much as Sophia did, or even more. So I think, and balloons are relatively cheap. So they're a good way to get kind of close to space without going into space. So I'm sort of optimistic.
Wonderful. Looks like we have another question from Julienne, who is a recent graduate from a UWC class of 2025. She finds astrophysics very interesting, but difficult nonetheless. And she was asking about potential university suggestions in her situation. Would you have anything to comment on that? Despite its not very
University,
traditional nature of the question itself.
Universities for doing a bachelor's degree or for a PhD.
I believe probably bachelor's.
It basically almost doesn't matter, I would say. So go to a school where the teaching is good. It's I think for undergrad, I made the mistake of going to Harvard, and I would never do that to myself again. The teaching quality was horrible. I think you're much better. You're better off at a school where you have professors who are actually interested in teaching.
That's a very interesting take, but I'd just like to ask because, of course, you asked if it's about the PhDs or bachelors. So would that answer kind of differ if I had said PhD?
Oh, absolutely. So I think for the PhD, you have to go to the institutions which are at the forefront of research. I mean, that's where you want to be. But for undergrad, it really doesn't matter.
Wonderful. Thank you so much. I'd just like to remind everyone that
shoot me emails. Sorry. I just
no,
want
I
to
was
say,
gonna
like,
say,
if you have more questions, just email.
sorry.
Go ahead.
Right. I was gonna say, if anybody has any questions, feel free to raise your hand if you're in the Zoom meeting, or write them in the chat of whichever platform you're using right now to view the stream. I'm very, very sorry for interrupting. I did not mean that to happen.
I apologize.
Do we have any more questions coming
Okay.
in? I do not see anything. So if maybe how about we give it another couple seconds and we can transition to our next speaker. Thank you so much. Thank you so much for the talk.
Thank you for the opportunity. That's great. Thank you.
Okay, thank you so much. I guess we can move on now. We've already learned a lot. Thank you. If you guys would like a short break, please take a moment to fill out the poll we just sent. And while you're doing that, I'll introduce the next speaker. So we move now from the US to the UK. Yasmin Hills, a 2019 undergraduate of UWC Southeast Asia, is currently halfway through her PhD in plasma physics at Imperial College London. So far, we've explored quantum physics and astrophysics, and we'll return to those topics later. Plasma physics is closely connected to both. It plays a key role in space and astrophysical phenomena, while also offering critical applications in nuclear physics and engineering. Yasmin will introduce us to one of those applications, laser-driven wave field acceleration, a plasma-based alternative to conventional particle accelerators. Unfortunately, Yasmin couldn't be with us today, but she kindly recorded the presentation. If you have any question, we'll still do our best to answer them. So let's dive in.
I'm Jasmine Hills. I'm a second year physics PhD at Imperial College London. And I went to UWC up until 2019. I really had a good time, and it's where I initially fell in love with physics. So yeah, I'm going to talk about laser plasma interactions for particle acceleration. I'll try and keep some of the more difficult bits brief, but there will be, I think, enough depth. So today I'm going to talk about motivations of particle acceleration, some theory so that we can understand further bits of the talk. I'll talk about what our group does and the applications we're looking at. I'll give you a taster of our research, and then a day in the life as a PhD student. So why do we want to accelerate particles? There's a really broad range of reasons to accelerate particles. I think the things people don't necessarily think about are the particle acceleration to enable research items. So this includes generating really short pulses so that you can investigate really small and short period natural phenomena. They're used for medical applications, so this involves radiation therapy or hadron therapy and medical imaging, industrial applications like sterilizing equipment, and they're used to generate synchrotron light sources. So this would be like at Rao diamond light source. And this is for studying proteins and crystal interactions. But the thing that people, I think, most think about when thinking about particle accelerators is the Standard Model and the Higgs boson. And we're now pushing towards further goals looking at the Standard Model. So how do particle accelerators work? Essentially what you have in a conventional accelerator is an oscillating field. You place the electron at the right point in this accelerating field, and you can accelerate that electron, or any particle using. The issue with this is if the field is high enough, it'll generate a discharge. This discharge will nullify the field. So this is when, essentially like lightning, you move from the negative side to the positive side, an electron current flows, and this nullifies the field. So what this means is when we want to scale for energy gain in particles, we need to scale the accelerating length, not the accelerating fields. Unfortunately, this means we have to generate gigantic accelerators. The next generation of proposed accelerators include the CLIC and the FCC. These span up to 50 kilometers, and between them will cost around 40 billion Swiss francs. So this isn't entirely sustainable as a way forward. A solution to this is using ionized materials. So ionized materials can sustain accelerating fields that are 3 times the order of magnitude of conventional accelerators. Ionized materials are plasmas. So you guys have probably heard about plasmas before. It's the fourth state of matter. And what it really is a material that's had enough energy put into it such that it's ionized. And what this means is the negative charges and the positive charges have separated. Now, if you were to look at something like this is my version of a plasma. There's tons of protons flying about and there's tons of electrons flying about. But from a distance, this looks like it has no charge because the same number of protons and electrons, and therefore they equal out. However, if you're close into it, you can see that there are unique charges moving around and responding to each other's charge. So this can be sort of characterized through several values that are the plasma properties. One of these is the plasma frequency. So this is the frequency at which an electron that is displaced in the plasma would oscillate if it was displaced. So essentially what would happen is if you moved an electron from the plasma, you'd be left with the plasma with a positive charge, +1, and the electron with a negative charge, -1. And these two, obviously similar charges attract. The electron would be drawn back to the plasma. It would overshoot it, and then it would continue to oscillate. This oscillation is simple harmonic motion, similar to a pendulum. The Debye length is the distance over which you would have to be before you saw only a neutral plasma. The collision frequency is how frequently electrons and ions collide, and electrons and ions have their own thermal velocities. The important thing to take from this is that plasma properties are denoted almost entirely by their density and their temperature, and these are really important in terms of how you can use them. So how can you use plasmas to generate really high electric fields? What you can do is you can separate out all the electrons and the protons. This will result in all the electrons being attracted to the protons, and then overshooting them, and then oscillating back and forth. But it will also generate a really high electric field because you have this big separation of charge. So here's how we use them. So we use a laser to push electrons out of the way. The electrons move faster than the protons, so that leaves all the protons where they are. Then the electrons are attracted back by the protons and then oscillate. What this means is you generate really, really high electric fields. Using lasers to do this used to cause somewhat of an issue. So when this was originally suggested as a way forward, it sort of lied dead for about 10 years until we had enough movement in laser development that this was actually achievable in a lab. So the way that this was made achievable was through chirped pulse amplification. And what this meant was that we could take a laser pulse, stretch it out, we could then amplify it, compress it, and then have a very intense laser pulse come out. The reason this needs to happen for us to amplify a pulse is that if you put a pulse in without stretching it out, it can get so intense that it will damage your amplifier. So to get through this stage here, we had to stretch it out before amplification. So what this did is enable the development of high intensity lasers and in turn, the development of wake field acceleration, which is when you use these lasers to generate really high electric fields and accelerate particles on them. There's been significant progress in wake field acceleration since it was suggested, and we are now at the stage where we're going to places and commissioning wake field acceleration beamlines for people to use practically. The near-term uses of these electron beams include XFELs. So this is where you have it's called an X-ray free electron laser. What happens is you take this electron beam and you wiggle it. When you wiggle electrons, they emit X-rays. So you can generate really coherent sources of X-rays. And this is used for scientific research or for medical solutions. The other thing you can do with them is very high energy electron radiation, which basically is when you target very high energy electrons at a tumor or a source of cancer, and it kills that tumor without killing the surrounding matter that you want to preserve. And this is called the flash effect. So there's a lot of near-term applications for these beams. So that brings us to what our group does. So we do laser-driven wake field acceleration and plasma optics. What this involves is the development of really short pulse, high power lasers. We look at optics with short lifetimes that can deal with high intensities, and we generate electron beams over really short scales. So I'm going to talk now in a bit further detail about a specific problem, and I'm going to use this because it shows the breadth of the kind of work you can do and the opportunities to learn about different things. So I will start with this. I'll go over wake field acceleration just again. So this is a gas cell. This is not ionized yet. What we do is we put a laser in there. The laser ionizes the gas. This laser also then generates those electric fields we were talking about. These electric fields, if high enough, can generate injection. If the electrons that you've injected, these are electrons from the background plasma that get injected onto the accelerating fields of the laser. If they're injected in the right place, this results in the electrons accelerating, and the length of which they need to accelerate is centimeters, because the the gradient of the electric field is so much higher. However, this is not a perfect field, and there are many issues with gaining high energy. So the problem we're facing is that the laser pulse traveling through a plasma travels at just under the speed of light, but the electron bunch that you're accelerating travels to the speed of light. What this means is that eventually your electron bunch outruns your laser pulse, and you can no longer accelerate it. Another issue we have is that the laser will eventually run out of energy because it gives off all its energy to the plasma. So a solution to this, which has been demonstrated at the Berkeley National Labs, is called staging, where you essentially put multiple accelerating cells one after the other. So you have one cell in which you inject electrons, you accelerate them, you transport them to a second cell, and then a second laser will accelerate them again. This sounds fantastic and simple in premise, but unfortunately, using lasers really, really close to focus, so close to really high intensities, is quite difficult. The box here that says coupling optic can't be a conventional mirror, because if you have a conventional mirror there, you would immediately burn it. And so instead of that, we use something called a plasma mirror. Plasma mirrors are interesting. They basically are mirrors built to burn. So you have a normal tape. So this is like a very small like film tape or like elastic tape, and you hit it with a laser. This laser ionizes the tape, so you end up with a plasma. And then the laser can be reflected from the surface of the plasma. And then you can basically just use that as a normal mirror. And this would all be fine and dandy if not for the way that lasers look in real life. So lasers have something called ASE. They have amplified self-emission or spontaneous emission. And this means that they have a lot of intensity before the main part of the pulse. So this is the actual laser pulse up here, but this is the time before the laser pulse arrives. And it's, as you can see, it's got a very messy amount of intensity before it. And what this results in is the ionization of the surface way before the actual main pulse arrives, which means you end up with a messy pre-plasma in front of your actual plasma mirror. You also have to be very cautious of the plasma mirror being bumpy and rough, so we are very careful with that. So we did an experiment with these plasma mirrors a few years ago. And this involved this complicated looking beamline, but it's actually quite simple. So we've got a little spherical mirror here that's focusing the beam just after the plasma mirror. And then we're imaging this focus to see what our beam looks like after reflection. And we saw that as we increased our intensity of the incoming beam, we saw a drop in the reflected energy in the focal spot. And when we saw our increasing intensities, our spots looked worse. So our reflected spots looked worse. So that's what this looks like. This is our laser. And I think you can tell pretty qualitatively that the spot looks a lot worse here. There's a lot more energy outside the center. Whereas here, you have a much more neat looking spot. This is important because if we want to use these to drive accelerators, they need to be good looking spots. So we tried to work out why this happened. And looked into the distortions of the tape surface and whether or not those could have been causing our really ugly spots that you see here. And this kind of gave us a good excuse to use machine learning because I suppose everyone wants to do that nowadays. So to try and reconstruct what the surface of the tape would look like, we used neural networks. So I'm going to talk about neural networks very briefly. I'm going to talk about them in the most simple way you possibly can, which is linear regression. So if you using neural networks, you essentially want to map some input into some output. So this is some X to some Y. And let's say you know that X and Y have a linear relationship. You know that Y and X will come in some relationship like Y equals MX plus C, which everyone will have heard of. So instead of that, I'm saying A1, which is our Y, equals W1 X1 plus B1. So that is, my X1 is times by a weight and added to a bias. I calculate what this value is. I compare it to what I'd expect that value to be. And the difference between the two of them is the loss. So that's how different our network is from what we want it to be predicting. We then calculate how the weight and bias change with that loss. And then you just tweak those weights and biases such that you can reduce this loss value. And once you get that loss value to 0, you'll have your network will predict your Y1 out of your X1. Actual neural networks basically do the same thing, but with vectors and a load more nodes and a lot more parameters. But the idea is the same. It's always matrix multiplication. If you've done linear algebra yet, you would be able to do this and work out all the maths behind these. So for us, we're dealing with image data. And so this is how an image is represented in a matrix. You have these pixels, which tell you the intensity of each of the values. And this is like a normal grayscale image. If you took an image of yourself and put it in gray, this is how it would actually be represented. And the way that neural networks work is they try and pick out the details of this image. The way they'll do that is you'll have a kernel, and this is a filter, and this filter just gets run over the image to try and extract features. So what our X and Y look like are the focal spot, the ugly focal spot we were talking about before, and the surface that we would see at the tape. Generated a bunch of these focal spots and surfaces using Fourier transforms, and then built a model to try and see what the tape surface would look like. And we found that the distortions on the surface of the tape were not the same as what you'd expect from a rough surface. So that kind of doesn't solve our problem. But what it does is motivates a different solution. So this is using a simulation, PIC simulations, which are when you have a particle on a grid, you find that particle's location and speed. You would then work out what forces that particle would experience on that grid. You would give them a little kick as a result of those forces. Then you'd work out where the particle is and what its new speed is and start the process all over again. So it's just moving particles around as though they're on a billiards table. So I did this for our plasma mirror with increasing pre-plasma lengths. And what this results in, I mean, you can see here, this is the simulation. This is the laser coming in and being reflected from the surface. And here is when you have a much longer plasma ramp. You can see as soon as you have this pre-plasma, the spot quality starts to get really bad. You see the kind of behavior we saw in the earlier focal spots. And you see filamentation. So that kind of illustrates a discovery process. Here's a bit more of a fun part of the experiment. So we actually did use these spots to try and produce electrons. And this is the setup. Don't really have to pay attention to it. The idea is you have the same thing. A laser is being reflected from a tape, but we've put a gas cell in front of it. And we generated really high energy electron beams. So that it does work. But it could be improved with better spots. But that is a question for another day. But the idea of this is just to show you that every bit of data you have becomes a kind of exploration. You have to try and work out what worked, why it worked, and what to do next. And that involves a lot of data techniques, understanding, and talking to experts in their field. So everyday computational work can be incredibly broad. So the data analysis we did for this was very wide ranging. It ranged from machine learning understandings to actually just exploratory data analysis. The actual work we did to get these results was 8 weeks of experimental data at RAL. So that's one of the oldest experimental areas in the UK. This work has been presented at a number of conferences and is going to be included in a paper or two. But this has involved like being able to talk through the work, being able to like communicate it, but also it's given me an opportunity to go travel. So I went to a conference this year in Ischia. I went to one last year in Hungary. You really do get to like go to a lot of different places. Yeah. So yeah, thank you for giving me this opportunity to talk about a bit of my work. I want to emphasize that, you know, doing a PhD, going into research means you get to do a really diverse set of things. It means exciting opportunities for travel, and you get really unique experiences, and you get exposure to really interesting and cutting edge topics. And I hope you guys, you know, go into the sciences. Yeah, thank you.
That's why I at least said in my recommendation to like reach out to current students in the exact department you want to go, because that changes like a lot of times. And I know for Chicago, like the physics department is pretty solid on average, just like some bad teaching apples. But yeah, I mean, I couldn't speak on Harvard, so I haven't been there for undergrad. But yeah, I would say like on, but I think this is a reputation that a lot of top research universities have, and it's something you should like kind of weigh in your head. Like, do you want the best teaching? Then you should maybe like look at other like liberal arts or other places. But if you want like a place with good teaching, but you have access to a lot of great research opportunities, and you can kind of make up the lack in the teaching part in your own self-studying, then maybe I would say like the elite research institutions have the edge there. I would just say, yeah, that's why in my answer on the chat, I said everything is like factors, right? So have the teaching quality as a factor as well. Don't just look at reputation and prestige.
I can probably add just one more thing also related to research. So I actually went to Middlebury College, so on the other side of the spectrum. So I went to a small liberal art college, and in fact, the teaching quality I could attest to is very great, because actually a lot of our classes, so my upper level classes, for example, usually have like 5 people. The downside is you cannot miss class. They will know. So you definitely need to go to classes, but also that also means the teachers really, really focus on teaching, and the quality of the lectures are always very good. The other thing though is that when it comes to research opportunities, I must say that smaller institutions like Middlebury College tend to be able to offer a bit less of those, just because of the sheer number of professors. So our department, I think, had something between like 8 or 10 professors, which also means that the fields of research that they are in are a little bit more limited compared to bigger institutions. And that what that means is that then you tend to be able to you tend to like have less opportunities or exposure, at least, to different kind of subfields in, say, physics or any other fields that you choose to go into. And that's also one kind of drawback when you compare the smaller institutions compared to the bigger institutions. So yeah, I think there are definitely like pros and cons, and I think it is a holistic decision that you need to look into to make, in terms of what do you prioritize in, or what kind of learning style you have, basically, or what opportunities you are most interested in terms of choosing which school to go to.
Thank you.
Thank you. I think I'll bring up a question that was sent in the chat, somewhat targeted to me, but Alex M. Stanek is asking, why does Brandon think more UWC students should go to Bates College? And I think, yes, I think Bates College as an example of a small liberal arts college is a great option, and people should consider it. I will answer it a little broadly, as in why I think UWC students having an option to go into a liberal arts colleges is a good idea. And I think it resonates with a lot of that has been said already. As from my experience, I just graduated with a bachelor's at Bates College in both physics and neuroscience. And something that I think has been a very significant strength is the faculty to student ratio being much different than what you would see at a large institution. Going to conferences and meeting other people from other institutions, and you hear about these classrooms, these lecture halls with hundreds of students, whereas my largest class was probably organic chemistry with like 50 students. And most of them tend to go from 10 to like 20 students maximum. And so this ratio allows for a deeper learning, deeper interactions with the faculty, better networking. Here is almost a given that professors will learn all of their students' names, which I had taken for granted until I heard about large institutions. And so it allows for that. And while on the one end, I think research opportunities, perhaps in terms of which fields are available, which themes are available, they may be more limited because you have smaller departments with fewer faculty, so therefore a smaller number of fields of physics may be covered, or astronomy. You have, in a small liberal arts institution, as an undergraduate student, you are the research assistants that they can have. You don't have to compete with graduate students for research assistant positions, and so you get this more hands-on and very deep level of work early on in your career. I stayed here at Bates during every summer during my career, and doing research on campus. In fact, right now I'm still on campus at the summer after graduation, still working as a research assistant. So I think it's a great thing to consider for an undergraduate, UWC graduate, or from anywhere else to go to a liberal arts institution that has good teaching reputation in the field that you're interested in. And consider Bates College. It's great.
Hello, I'd just like to say that after we are done with this this question session, we're gonna have a very short 5-minute break. Sorry for the interruption there. Just nice to know for the audience.
I actually, since you brought up research opportunities earlier, I was wondering how you went about securing them, both at your own institution, but especially at other places.
Okay, should I start?
This is an open question. Oh yeah, you guys.
Maybe Attila can
Yeah,
start.
so I mean, for
But
me,
yeah,
it was, yeah, I start. It was a long time ago, but I mean, you know, so this is the advantage of being at a research institution. There's lots of places, you know, lots of places for undergrads to be involved in research. So, you know, in some sense, it's, you know, there's ads around, but also, like, you know, if something is interesting, talk to your professor. You know, if you are taking a class and you have a professor, ask them what kind of opportunities they have, if, you know, or they know about. You know, most of them do research, and most of them want undergrads to be involved.
Yeah, I can echo that. I think one of my biggest regret in college is not knowing that you can start research basically at any point, like from the first year, the moment you step your foot into your college, for example. At that point, maybe it would felt like, wow, I don't know what is interesting, which is probably true and very natural since you don't know much about the field yet. But that's okay because the opportunity cost for first year is usually pretty low. So just, you know, you have the time, just go and ask the professors. And many people are actually very willing to take in first years because they want to have you for a long time. So you can, because they know that it does take time for you to get used to the field and, you know, learn more about the subject matter. So reaching out, asking people, just cold emailing, expressing your interest. You are an eager young person willing to learn. And I think a lot of people like that. So just, you know, reach out. And the other thing I was going to add is just that there is definitely this recognized like difficulty that is added for international students sometimes, for example, in the US, because many of the fundings do kind of allocate for students who are actually from, you know, the US itself. That said, it is even more important that you know, reach out to people who are also UWCers, international students who actually do know about some of these other opportunities. And some schools might not have like the full funding for you, but they tend to be able to kind of offer you a little bit of something to help you, say, do a summer research with a professor, if the professor is interested in, you know, working with you. Things can be arranged. And also there are many kind of, you can do research in as deep or maybe just a little bit more of a smaller project. So there are different ways that you can make that work as well. So I guess the biggest regret would always be that you didn't ask. So I would say just, yeah, go out and ask people, express interest, talk to people about what their research is about. People love talking about that. That's probably why everyone is here talking about our research. So yeah, so just reach out and ask is basically, I think, the advice that, again, I wish I had given to myself earlier.
Yeah, I agree with all that for the in university, and then like for outside your university, there's a lot of like online portals where you can apply for like summer research fellowships. Like one thing I highlighted in my talk was that I'd been to Caltech for the summer undergraduate research fellowship, and from my knowledge, that's like one of the most open, in a sense where like, they take like more undergraduates for their research fellowship than they have undergrads in their actual campus. So it's a very like big endeavor that they have, and like people from all over the world come, and it's a really cool experience. So I would say that's like a great one to try, like apply to, like reach out to professors at Caltech if you can visit them or talk to them, and go for a summer there. Otherwise, when I went to Harvard for the summer, I had actually just cold emailed some professors I wanted to meet, and then went there during my Thanksgiving break to meet them, and then talk to them and convince them to take me on for the summer, and they agreed. And like I had some connections from UChicago professors as well. But I think that was just me trying because I really liked their research for the neutral atom array stuff. So, and it worked out, so I was really happy. But so I think, yeah, like everyone was saying, like just try and ask. They won't be mean, and like make fun of you. At worst, they'll just say, I don't have space right now, but thank you for your interest. So you don't need to be worried about anything. Just like, yeah, just try whatever you're interested in, just reach out to people and people will be happy to try to help you.
Thank you. Yeah, I think that's some advice I'll have to take. Cold emailing professor, especially in Europe. I think I'm the only one here who was actually studying in Europe. And especially in theoretical physics, it's a bit harder to find internships from what I've seen. So yeah. Was Attila gonna say something?
Yeah, I just wanted to add that, like, if you want to go to grad school, it's actually like it's also your ticket into grad school in many ways. Like, it's much more important than your grades or your GREs. Like, that's basically, if you are working on research in a lab, that recommendation letter is probably going to be the one that will earn your space in grad school. So don't be shy. Go for it.
Thank you.
Thank you so much, everyone. And I believe now we can have a 5-minute break. So feel free to go to the washrooms if you need, and we'll be back in 5. Thank you so much.
Please note that this break is optional, so we don't expect everybody to leave. You can stand by. We'll just quickly be back. Yeah, just that too.
Okay, since you're here ready, Thi, just before the break starts, someone actually had a question for you if you're ready. Could we?
Sure, yeah.
Yeah.
One question.
So we're wondering about how you feel as a woman in STEM, whether you think that gender bias is very present, how it has affected you, and how women in general handle it.
Yeah, that's a good question. And I guess I should talk to physics in particular, because every STEM field is also a bit different. So unfortunately, like even though a lot of progress has been made in the field, the statistics right now still sense that at I think around 20% of PhD holders in physics are women. And yeah, like if you go to any faculty in a physics department, at least in the US where I know a bit more of, you can see that the ratio plays out pretty correctly. So there are like probably about 10 to 20% of faculty that usually are women. And it does like show itself. You can feel that, usually in the room, like for example, in my upper level classes, which we just mentioned a little bit before, in a small liberal art college, a lot of my upper classes, I was the only woman in the room. For many of these classes. So yeah, and sometimes you focus on your work and you don't really notice it, but some other time you just realize, oh, actually, wow, I guess no one else around here looks like me. So yes, it is definitely a thing, and thankfully, from what I can see, there are definitely at least less explicit discrimination in terms of like the day-to-day interaction. There are definitely, I have heard of many of these stories, kind of from people who are of an older generation. So progress has been made in that sense, but of course you still know that yes, you are kind of a minority, and sometimes it does take a little extra effort for you to kind of bond with people or to be part of a community as part of a minority in the field. So yeah, I think that is definitely a reality that is true. There are many people who are trying to make effort on it. There are some people who are trying to make effort against it in the recent, events. But I guess I can say that definitely, at least in my experience, what has been very helpful is at least that usually you can find a community within, this bigger field or community to have people who maybe have more aligned views or even just more kind of similar personalities or things that you care about, that you can bond with. And that is usually a very helpful experience to have in order to have a support system for you to go into the field as part of the minority. And just being, again, like it's the same thing as like, I don't know, UWC is usually kind of like a small group of people that you sometimes find in different institutions. And having a small group of people sometimes are actually very helpful because you can connect with people a bit better. You can actually bond with each other and help each other out in a bit more of an intimate way. And I have found that to be the experience sometimes with some of the more like kind of minority oriented groups in my field as well. And that has also been helpful. So yeah, the fight is still there, and we are, I think there's still more and more effort being made to make the field a bit more welcoming and equitable to everyone. But yeah, and there are ways that we can find to also make ourselves feel more at home in the field. And if any of you are interested in that, definitely reach out, and I would be happy to share more about the experiences as well as some kind of maybe advice or anything if you need to navigate the field as a minority. We definitely need more women in the field. So please do reach out to me.
Wonderful. Thank you so much, Tai. Oh, yeah.
Just before we move on, did Attila want to say something? No? Oh, okay. Thank you. Then yeah, sorry, yes.
Thank you so much. With that, I think we can get to Thai's talk. We already had the pleasure of hearing her speak, but as a gesture for formality, we should still probably introduce her. So Thai is a person who always follows her interests. This habit of hers, however, led to a rather unconventional background. She started off as a humanities student in Vietnam, and then boldly chose physics HLNIB and is now pursuing a PhD in physics. She is now following her interests, as per usual, in researching quantum optics at the University of Colorado. creating quantum light sources and probing phenomena are part of her day-to-day lives. And I think it would be wonderful to hear what she has prepared now about the particle nature of light.
Okay, does everyone see my screen all right? Okay, okay, I'm seeing it popping up. So yeah, so hi everyone. My name is Thi. I am a UWC from Vietnam, as it was introduced, and right now doing a PhD in physics. And today in this talk, I will be taking you on a little bit of a journey on like kind of the story of how humankind has come to understand light, this very familiar yet sometimes very weird phenomenon throughout the history, but also where we are at our understanding right now as with photons, light particles, and also sharing a little bit about what I do about that knowledge in my research and what I hope to find out more and what I hope for us as every one of us in physics to find out more. So the story started with me as an undergrad working in Middlebury College, and I was working in the quantum optics lab. So thankfully, multiple of the previous speakers have introduced quantum to our audience today. But as a recap, so quantum is basically, you work with this like discrete, small, level of energy or particles. And when it comes to optics, so quantum optics is the field I work in. And when it comes to optics, you talk about light. And if you work with a very small amount of light at a time, what you have to do is you usually have to keep your lab very dark. So most of the time I work in the darkness because we want to see this very, very like little packets of light. So when I work with my advisor in Middlebury, we used to have this joke that before we turn on the light in the room in order to see our way, and in order to not like blind each other, what we usually say out loud to each other is 1, 2, 3, photons. So photons and photons indeed, like if you just switch like the light switch, then suddenly like trillions of photons will come flooding the room, like almost instantaneously. And that's actually a fact that is usually overlooked. It's actually a very amazing feat in humankind because our ancestors did not enjoy that luxury. They, had to build fire. It took them quite a long time to learn how to do that. And light has always been this kind of phenomenon that is very celebrated, is like people are curious about it. Light represents many things, like Renaissance is all about like learning about light, and light is like enlightenment, like, in a lot of different cultures, it is a very, kind of hopeful symbol, and light is good against evil. Light is just really a very important and, celebrated phenomenon for us humans. And that's why when we are able to create light, that was actually a big chapter in our development. So suddenly we can create this like mystical source from the heaven. We can control it, we can have it, we can see our world so much more clearly. And suddenly once we figure that out, light is now everywhere. Light is on your screen, light is on your phone, light is like, everywhere right now, so much that I have to block them off so that I can sleep at night. So this has been a very big step forward for humankind. We know how to kind of use this force of light, but also we understand light better. So many people have started asking, what exactly is light? What is a light ray? What's the difference between light that comes from the sun compared to light that, comes from other sources like artificial sources? So all of these questions also lead to understanding that help us see the world better. So we can now understand how to put lenses together to look very far away. So for example, in the previous talk where we, look at stars and galaxies and these very, very far away things that we would not be able to see before. And we can also see very small things. So microscopes can help us now see, cells and even atoms. And so understanding and being able to use light help us see the universe and help us understand it and help us live better in the universe as well. But so that's like all very exciting. But for the scientific community, I think the more exciting invention is actually the lasers. So here I have another kind of, little story about UWC actually. So this is my origin story in my physics career. So in my physics IB course, which again, I don't know why I chose so boldly at the time, but definitely a very good decision. I had a really good teacher in UWC Dilijan. Ritik is definitely one of my favorite teachers of all time and is very instrumental in helping me, start this career. So I owe a lot to UWC to that. But he was showing us this like kind of pretty, classic experiment that a lot of people shows in physics labs, which is the double slit experiment. So if you've seen this experiment before, when you shine laser light through this like card, which looks normal on, kind of at an eye level, but actually has these very tiny slits on the card. Normally you shine light on something, you see a blob of light, but in this case, you don't. You actually see this pattern that happens when the laser passes through this double slit. So this double slit experiment shows something about light that we just don't understand before. Like it's not just a ray from the sun. This is actually, there's something else that's happening here. And this is only possible because we have the laser and we are able to create this very precise experiment. So when I saw this, I asked my teacher Ritik, what is laser? Like what does it do it? Like how can we see things? Because the laser is like this. So Ritik has a moment, like he looks at me and he was like smiling very cryptically and he was like, well, you should go find out. So it's one of these like, teachers moments. But it actually launched a whole career. So I don't blame him for that. I mean, looking back, I think maybe he didn't know how to really explain to me at that moment because, well, to be fair, this is a very complicated thing to explain on the spot to, an IB student. But now that I know a bit more about lasers, I realized that, yes, one of the way that we can say why laser can do this is, well, if we were to answer briefly, it's about coherence. So coherence is like usually kind of compared to this image of soldiers marching in lockstep. So when one person walking, it doesn't really cause too much of disturbance, but when many people walk together and syncing perfectly with each other, suddenly there's this collective behavior that create a very, very strong force. And it's kind of similar what happens in the laser when you have these light that you are creating to be very in sync with each other. They build up on top of each other and create this very, very focused, very strong source of light. This coherence actually enables us to see one nature of light that we didn't see before, which is the wave nature of light. So when you kind of see this, like you can describe this behavior as a wave, you can see that they can actually add up to each other. So if you have two waves and you can add all the troughs to each other and all of the peaks to each other, then you suddenly have this collective behavior. And this coherence actually enables us to see a lot of different phenomenon. So what we just talked about is a double slit experiment, which can only be understood because we can see that there's a wave nature to light. But we don't stop there. What we continue to see is that we understand that, okay, now we can kind of have this paradigm shift. Light is also a wave. You can suddenly explain other phenomena like thin film diffraction. Why is there rainbow color on a bubble? And, rainbows, like, I don't know how people can sleep at night before they understand how rainbows work. You always see this beautiful thing in the sky and you just don't know why it happens until you realize that light is actually a wave. And with many, many different colors of light, when they diffract, when they interfere with each other, the position is different. And that's why it creates a whole rainbow. So again, our ability to understand light and to even kind of create it in that property, so being able to create the laser has enabled us to understand the world, but also to advance our technology. So in the first chapter, you see that once we can create light is suddenly everywhere. You can use it for many different purposes. Now, whether you know it or not, lasers are also everywhere. It is in all kinds of different technologies in our daily life, from our printer, our reader, in our medical procedures, but also in our lab, we also are able to use our lasers to create very, very precise experiments. So for example, here you can see that we are using very narrow laser beams all aligned perfectly to each other to trap one atom in space. And you can even have what is called an optical tweezer. You can pick up an atom, you put it in a place as you want and create this like pattern. So this is created in the University of Chicago. So you can see the Chicago beam there. You can also create all kinds of other different technology and experiments that are possible because of laser. You can transfer information across vast space because laser and light is one of the most efficient way that we know of to transfer information. You can also detect spies. That's of interest to some government maybe. So obviously laser is very important. So here, I hope that I have painted a picture of like some of the kind of development of our understanding of light and how that has enabled us to understand the world and also to advance our technology. So now on to the third chapter. Oh, before we go to the third chapter, I have a little quiz for everyone. So a photon walks into a mirror. In other words, you shine light onto a mirror. What do you expect to happen? So if you have looked into yourself in the mirror this morning, probably you have observed this. So the photon would come to the mirror, bounce right back off. That's how you can see your reflection from the mirror. So nothing, special here. But here's a real question. What if a photon walks into two mirrors? What if I place another mirror behind the first mirror? What do you think will happen? So the most conventional way of thinking about this, yeah, I'll give a little bit of time for people to think or just to guess. I mean, this is not a very accurate physics question by any stretch, but just wondering what people would think. So normally, I think people would probably what we would expect is like from our intuition is that, well, it will be the same thing, right? The photon would just come to the mirror, the first mirror, and because it didn't ever pass to the first mirror, it would just bounce back, and that's it. But what actually happened and what I see in some very specific cases, and what I see in my lab basically every day, is that this photon actually passes through both of these mirrors. So how does that happen? This is definitely not something that you can intuitively understand from your normal everyday physical, experience. So what actually happens is hinted at before. This is something that you can only explain with the wave nature of light. So what we create by putting two mirrors together at just the right distance is actually what physicists call a cavity. It's a bit of a misnomer. So cavity sounds like it's just, empty space, but actually it's doing something more than that. So when you have the two mirrors at just the right distance with each other, so say you have a first mirror, you shine light on it, and you move the second mirror back and forth, and at a certain point you hit the right length, then you suddenly see all the light transmit through. And this is a wave phenomenon that has to do with conductive interference, as has been mentioned before. When you have the length just right, the light that goes from one mirror to the other and bounces back actually adds up to the previous light that enters, and that creates a standing wave, this constructive interference that helps build up the energy inside this cavity and also helps light transmit through to the second mirror. So this is totally a magic trick, right? Like I do this all like every day, so sometimes I kind of forget how cool it is, but it really is a very cool magic trick because when you have one mirror, nothing goes through. If you have two mirrors, then suddenly everything goes through. And again, this can only be explained because we understand the nature of light as a wave. And also this will be a bit more relevant to the next part of the talk. So that's why I brought up this little quiz. So now we are truly going to the third chapter, which is basically more of the title of the talk, the chapter of photons. So we've been introduced a little bit to quantum today, and photons are just quanta or discrete packets of light. So they are light particles. And they have these discrete and indivisible amount of energy, as in if you have a packet, it has a fixed amount of energy that it contains. And you have many, many of these packets. And the first thing that the first people that kind of formalize this concept of particle of light are people who were describing, and particularly Einstein, who actually won a Nobel Prize for this, rather than like special relativity and other great work that he did. But this is actually something that Einstein first proposed a description for, the photoelectric effect. What happened in this effect is when you shine light on a metal surface, for example, which has many atoms, what happens is that these light actually provide some energy to kind of knock off some electrons from the surface atoms, and that electrons can be ejected and we can detect them. But the weird part is that when we think about light as wave, when light hits a surface, as long as you just keep shining light, what you expect is that there will be, at one point, enough energy for these electrons to just jump out. But the weird part that people observe is actually that's not always the case. If you change the color of the light you're shining on, at one point, actually, there is no more electrons that jump out. This cannot be explained if you just think that this is kind of continuous energy shining. Of course, if you keep shining light, it will ultimately reach an energy enough to let this happen. But the fact is that light actually comes in these energy that has to do with its color, as probably many of you have heard about. And when it hits these surfaces, only packets that contain enough energy in each discrete energy packet would be able to eject these electrons. And the only way that we understand this is that light is actually a particle. It's not just a wave, but it actually has discrete energy level, and also known as quantum of energy level. So now we suddenly have this new understanding of light. It's not only just a wave, it's not just a ray of beam of light hitting like a mirror and come back. It's also a wave, and it's also a particle. So this duality of wave and particle now unlocked new understanding of what light is. And the next question is also, what do we do with that understanding, right? Like, okay, we know that they're particles, so what? So to understand that, the same way that people have made lasers, and how lasers have unlocked so much more understanding and research in physics. Now, the quest is to create a quantum light source. Now we want to create the equivalence of a laser, but can emit light in a way that we can see them as particles, not just as wave. So what's special about that? I mean, we are creating photons everywhere. At a light switch that my advisor and I can turn on, trillions of them come out. So what do we have to do to make a quantum light source? That's the question. So it turns out that the difficulty is not really about just creating light. You can create very, very bright light. The question is, how do we work with that light one photon at a time? So how do we actually see this light coming in, maybe at a stream, but we can still pick out, okay, 1 photon, 2 photons, 3 photons. And how do we manipulate each of these photons so that we can create experiments, and how do we work with those to understand them better? That is the challenge that we are dealing with here. And so one idea, it turns out, to be able to create such a light source is actually kind of similar to what we have talked about. We're exciting an atom or a system where we can eject, 1 photon at a time. So it turns out that atoms have these discrete energy levels. And when you excite the atom into an excited state, and when it comes down to the ground state again, what it does is actually it ejects 1 photon. So you shine light, you get some photons coming out. The problem still is that this atom is kind of emitting light in every single direction. How do we even kind of control and collect one and then use that photon, right? So that's also a challenge. And to answer to that challenge is actually, we will use something we mentioned before, which is a cavity, a photon box, in other words. So if we put 2 mirrors around this atom and we shine light to it, there are 2 different things that will happen. One is that these photons are suddenly now bouncing back and forth a lot in this box, which makes the probability of that photon interacting with the atom to be a lot higher. Now you have all of these photons concentrated in one little space, but also you are able to guide that photon and have it come more or less in the one direction, and you can collect that photon, and then you can use that for more useful purposes, like designing your experiment and seeing how that photon behaves. So that's kind of how people are creating these photon sources, which at least one of the ways people are doing that. And in my particular research, instead of using just like an atom, which many people, for example, people who work with neutral quantum computer can do, they can trap atoms in space using lasers and then excite that atom to create this light source. But one problem with that is that it is usually a little bit bulky. So you do have to have kind of, like was mentioned before, a whole table of a lot of different optics, and you are shining 6 different beams that overlap perfectly together to trap the atom. And you then keep it very, very cold to like microkelvin in order to be able to do that. Instead, in my lab, we are exploring something a little bit different, something called an artificial atom. Particularly, this is a quantum dot that is actually trapped on a semiconductor chip. So what that means is that this artificial atom is actually not just one atom. It is actually an island of atoms that contain 100,000 atoms, roughly. And when we create this island, what we actually still create is that there's this confinement, there's a space where there is like only particular resonant wavelength is used to excite this quantum dot. In that way, it behaves very much like an atom. So you have a particular wavelength where you can excite the atom to the excited level, or the artificial atom. And then when the artificial atom relaxes, it also emits a photon. And what that enables us to do is that we can actually create this very, very efficient light source. In fact, this is the most efficient light source right now in the field. So it can emit technically up to 1 billion photons per second. So it's very bright, and the nice part is that it emits that many photons, but only one at a time, because the artificial atom can only be excited once at a time. And when it relaxes, it will only give out one photon. Now, the question then is, how do we excite this quantum dot efficiently? And how do we collect all of these photons? And again, we design a cavity to do this job. And there are some considerations. What is the cavity shape? How long should the photon stay inside? How to collect photons from this particular structure? And in my particular experiment and what I'm studying, we use this particular structure of cavity called an open access microcavity. It's a microcavity. So all of the things that you see here are actually at a micro scale. So this little dome here is about 10 microns across, and this distance is about 2 microns. So they're all very microscopic, and you can't quite see it with your eyes. But what it does is that it does provide this structure where you can confine light in one space. You can make it interact with your quantum dot, and you can collect the light that the quantum dot then emits upwards to an optical fiber, and then you can use it for multiple purposes. This is what it looks like in real design. And the nice part about the system is that it is actually very compact. So it is about 1 by 1 inch in this particular footprint. And once I make the source, we can kind of package it, and we can potentially use it to ship it to another lab, or for people to actually use it as a single photon source to do whatever experiment that they would love to do, which is actually a pretty powerful thing to be able to do, because again, our goal here is to create basically an equivalence of a laser. We are able to create this tool that people can use to do all kinds of interesting things with it. So that is kind of the main part of my research, but I want to also zoom a little bit to give people a little bit more about like what else do we care about in terms of working with single photons. And every single little box on this slide is actually an active field of research that if you're interested in, I would strongly encourage you to go and find out. All of them are interesting problems, and both physics and engineering problems to solve in our lifetime. So we have a photon source, we have photons coming out. Now we also want to guide that photon to create meaningful, say, circuit to do something with it, right? So there are free space optics that you can use to do that. So you can collect photons, you can also direct them using mirrors and create certain interesting experiments, but you can also actually do something called the photonic integrated circuit. And this is the part where it's very exciting. So this is a picture of something that you can actually create on a microscopic scale. So the scale bar here is 5 microns. So you can create these structures, and you can create these circuits to guide light around and also interfere them, to entangle them. Even that's the buzzword I haven't mentioned yet, but these are all the different things that you can do. And now all can be done on just a chip. So it's a photonic circuit that you can build and create interesting things with it. And then the other part of it is detecting and counting. How do you even detect a single photon, right? Like you can see light with your eyes with so many light, but you cannot see one photon. But there are other kind of equipments that people are developing to do that. So you can detect single photons by using avalanche photodiode or superconducting nanowire single photon detector. So these are all very precise equipment that can count down to the single one photon. Every single one photon will get a click, and you can detect that. And that's alone, like I would love to, have a moment to appreciate like how technically interesting that is. And also, once you already detect that, you might have like a million photons that come together, and people can also find ways to count that. So this is a graph that, I make in my lab very, very regularly. So you can actually have, say, 20,000 photons that come at any particular second. And having the technology to count that is also a very interesting technology problem. All right, so I might be a bit over time here, so I would like to wrap it up a little bit. So we've kind of come through a few chapters in the history of our understanding of flight, and every single part of it, we start to understand our world a little bit more. So here are some kind of the milestones that I personally find to be my favorite. So the first time I looked through a microscope and see the cells in my skin, that was awesome, right? Like there's this whole world that exists kind of just under our eyes, but we just cannot see it until we find ways to understand light better. Then the next, this is one of my favorite, scientific photographs ever. This is a picture of a single atom that somebody can take a picture using actually just their DSLR camera. But the amazing part is that you can trap that single atom inside this little space here, and you can see the glow of that single atom, which is really, really amazing. And now we can also start seeing single photons. We can start seeing photons that arrive one at a time and kind of detect it and see its properties and all of that. So like the previous chapter, we understand the world more, but also what kind of technology will this unlock? Actually, there are so many that we don't know. Like, we don't know all the things that the lasers could do when we invented it, but there are many things that it can do now. So some of the technologies that at least are in the kind of in the book people are studying now is, first of all, quantum computing, which has been talked about today. So having single photons are actually one of the possible way of creating quantum computing platforms by using photons that can be entangled with each other, photons that can be used to build gates. And as I mentioned before, integrated photonic circuit is definitely one of the platform people are looking at to do this. Entanglement is the other thing that a lot of quantum physicists are interested in studying more about, and it is also a very useful resource, it turns out, to be used for different technologies, networking, information sharing, even things like astrophysics. When you have entangled photons, they can actually help with increasing the resolution of what you can see in outer space. So there are many things that you can do with this technology, and many more that maybe we don't even know yet once we actually can make the technology happen. So with that, I would like to conclude my talk. So back, again, like just thinking back to the story of the 1, 2, 3 photons that I were counting for fun with my advisor. Now I end up, counting photons one at a time in my lab. And I hope that when we advance the technology, which is of course based a lot on curiosity and understanding, it will also enable us to be able to do new quantum technology in the future. So that is basically the story of how we are hoping to shed light onto the quantum world and quantum technology one photon at a time. So yeah, that's kind of a story that I walk you through, but there are many details that I would be happy to answer if you have any questions about these different details and the research. Thank you.
Thank you so much, Sai, for this wonderful talk. Sorry, Faisal, you can go.
No, go ahead. Yes, that's fine. We just wanted to thank you, T, for this amazing talk. It was very engaging, and right now we'll be checking the Q&A for any questions. If Yasin would like, we have some questions prepared as well.
Yes, I was going to ask about the practical aspect of counting each photon, as you said. I am aware of the existence of multipliers and diodes that can be used to amplify the image, but I would imagine that there is quite a bit of interference that goes into that sort of stuff. So how is the detecting process? What does it look like? I don't believe we can hear you, Thai. T, I'm so sorry.
Okay.
So
All
sorry.
right. Sorry. Yeah, no. We thought we knew Zoom by now, but I guess not fully. But yeah, so I was gonna say that yes, this technology definitely exists and is actually working very well. So the avalanche photodiode that I mentioned is actually kind of very similar to the photomultiplying tube. So it actually works by enhancing the signal of a single photon by having this avalanche, basically kind of a chain of reaction that happens when a photon hits the detector. And that's basically how people can count it. And the other technology, which is even more sensitive to single photon, the superconducting nanowire single photon detector, is probably the leading technology right now in counting single photons. And they use superconducting circuit, which is even more sensitive to these, to having one photon arriving in order to count these photons. So people can actually count them very well. Now, you're right that there are definitely some challenges. So for example, when you kick off one photon, there is usually a dead time, for example. So you cannot just keep sending photons into this detector and hope that everything will be counted. So there's certainly some dead time that people are trying to reduce in order to count these photons even more efficiently. And we're talking about like a very small scale of time here, right? Like nanoseconds or like even smaller time. Actually, the resolution of the avalanche photodiode that we have is probably on the picosecond scale. So yeah, so basically, the short answer is that yes, we have ways to be able to detect something as small as a single photon. Now, the other challenge is how do we keep track of all of them? How do we make sure that they keep coming and keep being counted and we're not miscounting something? And also, yeah, even just the electronics, if you think about it, of how you can keep track of all of these photons are actually the other thing that you need to care about. Yeah, but it is doable in the lab these days. So that's kind of the amazing part.
Right. Another question that I had regarding the quantum dots, is there a way to combat this sort of downtime? I would assume that this is why you would want such a short burst of so many photons, as with the quantum dots.
Yeah, so the quantum dot is more on the emitter side rather than the detection side, right?
Right, exactly. So would you be
Yeah.
using the sort of short bursts of photons to mitigate this sort of downtime that you're talking about?
So actually, the reason why we want a fast, like many, many photons that come out at a time, because we want it to be bright and we want it to actually have efficient generation of photons. One application that you can think of that is actually some people are looking to make this as the new transistor in a way. So like you can create light and you can generate light very, very fast in order to use it to make circuits, to create gates and things like that. And what you want is that you want a source of light that is actually very fast. Can do that because, if you think about, say, gigahertz of processing power in a computer, for example, you want your light source to be able to be at least like kind of on the same level of efficiency. You can create this like signal very quickly. That's kind of why we want to have a very bright and very fast source. But of course, the challenge is then if we have this fast source, how do we work with it? How do we keep track of photons? How do we count them and things like that? Yeah, so we want it to be bright. We just want to know how to work with a bright source.
Thank you so much. And as we're waiting for more questions, I would also like to ask you one other thing. Is there a way to measure photons without necessarily converting them to electrons first?
Well, that's a good question. And I think right now, so actually the superconducting nanowire again, oh yeah, I was actually saying that this is actually not my field of expertise. So I work with the generation part. There are a lot of smart people who are trying to actively answer these questions. And if you're interested, of course, you should go and find out a bit more about how people are trying to solve these problems. So yeah, so the superconducting nanowire actually works in a slightly different way than just having electrons kind of being clicked and then you detect that. But I think the reason why electron is usually kind of the go-to is exactly because there are many of them, and so you can still have like this fast process of like a photon making an electron kind of decay into this avalanche cascade, and that's why people are using that as kind of the default to count these photons. Like basically the photons are too fast. Now you have to think about a way to have something that is also equally fast to kind of react to every time a photon comes. And then how do you detect that as well? So we know how to kind of measure electrons and measure electric current very, very efficiently. And that's why that was kind of the choice. Yeah, but that's an open question, whether there's any other technologies that might actually work.
Thank you
as
so
well.
much. I see that Attila has a question. Would you like to ask it?
Sure. So it's actually not a question. There's other ways to detect photons. So for example, some of the detectors that we use in far infrared astrophysics. So there's a bunch of detectors called kinetic inductance detectors. And so they actually convert photons not into electrons, but into quasi-particles. So, it's a different species of charged particle. But I think in some sense, you always have to convert it into some sort of a charged particle for individual detection. It doesn't have to be an electron.
Right. Thank you so much. Thank you so much. That answers it quite well. I'll definitely look into that later. Does anybody else have any questions?
If not, I think we could move on to our next speaker. We're a bit behind on schedule. We'd love to keep talking to you, T. This was one of this was one of the more engaging talks we've had so far. It was truly amazing. Thank you so much for your time and for your support. And now we'll move on to Vikram. All right.
Thank you so much.
Yes, and it is my pleasure to introduce the final speaker for the session, Vikram, who graduated from UWC SCA, Dover in 2018. He's an astrophysics PhD candidate at Steward Observatory at the University of Arizona, where he has been working on modeling multi-messenger emission from supermassive black holes. He uses a combination of high-fidelity numerical simulations, theoretical calculations, and observational data to attempt to shed light on fundamental processes around supermassive black holes and their evolution. Vikram's talk will teach us more about the opportunities that multi-messenger astrophysics opens up for understanding fundamental physics and how we approach understanding supermassive black holes from the theoretical side. Thank you.
Okay. Hey, everyone. Well, thank you for that introduction, Brandon. And thank you to the conference organizers for having me and for putting this on. It's really great to connect with the UWC community again. It has been a while, especially with the pandemic in the middle there. And so I'm really grateful to be here. So that was a pretty comprehensive introduction, but I thought I'd show some photos. So that's me. I, as Brandon said, was in the class of 2018 at UWC SCA Dover campus. I was actually there for about 9 years. We have K through 12 at that UWC. And so I actually knew Rohan, who was one of our earlier speakers, really well since we were about like 11 years old. So that's a fun connection. And then I graduated from Northwestern University studying physics with a minor in computer science, which turns out to be important. And now I'm doing my astronomy and astrophysics PhD at Steward Observatory. There in the top right is a photo of the original Steward Observatory. I think a few years after it was built in 1922. So we just recently celebrated our 100-year anniversary. And this is a photo I took with my phone on one of our neighboring mountains at one of our telescopes. And as Attila mentioned earlier, there's the Milky Way has like these dark regions at the center. And actually here, if you adjust your eyes long enough, you will be able to see the dust lanes in the Milky Way. So it's a small advertisement for coming to Tucson to see the night sky. Okay, so why astronomy? Why astrophysics? Like, why do I do what I do? And I'm sure a few people may have mentioned this at this point, but space is the ultimate laboratory. The universe hosts the most extreme objects, and the most extreme objects allow us to study the most extreme physics. And so, for example, in space, we found the strongest gravity. Everyone's obviously watched Interstellar, so this is not a real black hole, but I thought it would be good to start with somewhere that a lot of people have seen. The universe also hosts the densest matter, and so pictured here in the top right is a neutron star, and a neutron star matter rather would weigh about 1 teaspoon of neutron star matter would weigh about 10 to the 12 kilograms. For comparison, that's about 900 pyramids of Giza in 1 teaspoon, and so that is some seriously dense matter. Matter denser than anything we can find on Earth. We also see the hottest plasmas around black holes, which consistently reach millions, if not billions, of degrees Kelvin or Celsius. The largest energies come from gravitational wave events, and so this binary black hole merger that's pictured here in the right released about 3 solar masses worth of energy in its gravitational waves. And for context, that is about 50 times all the starlight in the observable universe released in gravitational waves. So just immense amount of energies. We also have the strongest magnetic fields. The magnetic fields on that neutron star to the top right, if it was a magnetar, would be about 10 to the 15 Gauss, which is 10 to the 15 greater than Earth's magnetic field at Earth's surface. And we have the fastest moving particles. So relativistic jets can accelerate particles up to near the speed of light. And finally, I mean, the universe is the only place where we can study the structure of the universe itself. And so here pictured is the cosmic web, which is like depicting the matter density in the universe on large scales, meaning like galactic to galactic clusters type scales. And so the universe really provides us with a really unique opportunity to test fundamental physics at the very limit. And so, speaking of limits, I'm going to be talking about supermassive black holes. And everyone's seen the pop culture reference in Interstellar, but I wanted to clarify some things about exactly what black holes are. And so, strictly, a black hole is defined as a region of space-time that is separated by an event horizon. An event horizon is a point at which no particle, not even photons, can escape to infinity. And so this is that classic point of no return that people talk about with event horizons. And up until recently, we had never seen a black hole. But I think, as Attila mentioned in his talk, the Event Horizon Telescope in the past 6 years or so has now seen 2 black hole event horizons. That's M87 star and Sagittarius star. And so what we see in the center here is the black hole event horizon. And around it is this hot gas that's radiating photons. And we see similar structures here. Okay. And so we can actually break down black holes into 2 categories generally. So we've just seen supermassive black holes, both in fiction and in real life. Well, we also have a second category called stellar mass black holes. And so stellar mass black holes form as the product of a stellar death. And so when a star that's massive enough, greater than 8 solar masses, finishes its life, means it stops burning in its core, it will collapse due to a lack of electron degeneracy pressure holding up the star. And so that's how these stellar mass black holes form. We don't really know how supermassive black holes form. There are a few theories that still need to be tested and still need to be discovered. But this is a really active open area of research, an extremely exciting one as well. Okay, so now that we have our categories of black holes, let's try to understand how we might actually observe them. So luckily first, black holes are pretty simple. They can be described by their mass and their angular momentum, or rather their spin. There's a third characteristic of black holes, that's their charge. Traditionally, black holes don't retain electromagnetic charge. That means like, positive or negative charge, because it's quite easy to get rid of charge. If I'm a black hole and I have a positive charge, I will preferentially eat up more negative charge. And so it's quite easy to get rid of charge. And so we can generally describe our black holes with mass and angular momentum. Okay, black holes are not that simple. So many of you may know black holes are a consequence of Einstein's theory of general relativity, where he described space-time as a fabric that can be curved and shaped by the mass on it. And so I think it was John Wheeler who came up with the really elegant explanation or interpretation of it, where he says that matter tells space-time how to curve, and space-time tells matter how to move. And it's described by this seemingly simple equation, where on the left-hand side we have our space-time, that's described by this tensor G. And on the right-hand side, we have a bunch of constants and this tensor T, which describes the matter content, meaning energy, mass, anything that can help curve spacetime. And so what this equation simply says is that matter will tell spacetime how to curve. I actually gave a public talk recently where I talk about the brief history and future of black holes. This is more oriented towards the public. And so if you're interested in learning about where black holes come from, I think you can find this on YouTube. So you just have to search Space Drafts 107. But the point being here that black holes themselves were not just due to one person, Einstein. There are a number of scientists that have contributed immensely to black hole science over the years. Okay, so we now know what black holes are. And we now know that black holes are well black. So the question is, how do we study them? If they're dark, it's going to be hard to see them with telescopes. So the trick is to add gas to black holes. Adding gas or hot gas to black holes lights them up. And so I'm going to be calling this accretion. And so accretion is the process of a black hole eating up other stuff. And generally, this is hot, not so dense gas that's formed from the death of stars, or not the death of stars, rather the tidal disruption of stars and interstellar gas. And this accretion will actually light them up. And so that's what we saw with the Event Horizon Telescope. What we see here in the outer edge is an accretion disk made up of hot gas that is lighting up the black hole, or rather letting the black hole cast a shadow on the gas. And when black holes accrete matter, they're going to launch relativistic outflows, like jets on galactic scales. And so what you're seeing here on the bottom left is an extremely zoomed out picture of M87 star, where we see the galaxy here of M87 with a relativistic jet beamed across galactic scales. And so this relatively tiny object in M87 star, the black hole itself, is launching these galactic scale jets. And so it's been an open topic of study, how these jets form and how they span galactic scales. This is not a unique phenomenon. This happens consistently across many galaxies that we observe. And so here's another observation of Centaurus A and the EHT, Event Horizon Telescope image of the jet structure at much smaller scales. So this is what we call electromagnetic radiation, right? So we're seeing photons from these systems. And these photons are telling us something about these black holes, telling us a lot actually about these black holes. But there's another way to see black holes. Orbiting black holes will produce gravitational waves. So when you have compact objects, which is a black hole or a neutron star, and they in-spiral and merge, they'll produce these tiny ripples in the fabric of space-time. I like to think about this as if you move your finger or run your finger through a pond and you see ripples emanating from that spot, that is what's happening to the space-time, essentially. Unfortunately for us, these ripples are extremely tiny. I mean, 1 part in 10 to the 20. I don't know about you, but I have no concept of what 10 to the 20 is. And so I did a small calculation to see what this actually means. And so it turns out that 1 part in 10 to the 20 is like measuring the distance from the Earth to the sun, changing by 1,000th the width of a hair. I can't really imagine measuring anything to 1,000th the width of a hair, let alone the distance from the Earth to the sun. And so you would think that we would probably let this problem be, probably leave it alone for a little bit. But we're pretty stubborn as humanity. And so we decided to try to solve this problem. And we did with what we call laser interferometers. And so I realized this morning that a lot of you would have taken IB physics. And so if I mention, so I can actually talk about how this works. And so you have a laser that's split and sent along 2 arms. That's those 2 arms you see here. These 2 arms are the same length. They are usually the same length. And so when those beams come back, they reflect off mirrors and they come back, they will destructively interfere, which means you'll see nothing. However, if you have a gravitational wave that squeezes spacetime, the path length will change in one of these arms. And when the light gets back to the original source, it will not have completed the same amount of phases as the other beam of light. And so you'll have some sort of other destructive constructive interference pattern. And so that's actually how we measure gravitational waves. And so in 2015, LIGO detected the merger of stellar mass black holes with this laser interferometer. And what you see here in the top row is what we call the strain, which is the change in the spacetime, 10 to the negative 21, right? 1 over 10 to the 20, essentially. And we see this actual ripples in the fabric of spacetime. And we saw it across multiple detectors. We have 2 of these. And we saw the chirp, essentially. And so this is the most robust evidence we have for Einstein's theory of general relativity being correct. Okay, so now what is multi-messenger, right? So I've talked about gravitational radiation here on the left, and I've talked about electromagnetic radiation. And when the same source emits both of these types of radiation, we call it a multi-messenger source. To be clear, in this image, on the left, I'm showing a stellar mass black hole merger, and on the right, I'm showing supermassive black holes. And so these are not the same source. These are just 2 examples of each type of radiation. However, we have had one great multi-messenger source. So this was the merger of neutron stars. So here on the left is an artist's depiction of a neutron star merger. We see the 2 neutron stars. They are about to collide, or they are in the process of colliding and releasing radiation. And so since neutron stars are compact objects, they emit gravitational waves. So we've already established that. And also because we have dense matter, we are going to see electromagnetic emission from these systems. And the combination of these 2 types of radiation allows us to do an immense amount of physics with this event. For example, measuring both the gravitational waves and the electromagnetic emission can actually tell us about the expansion of the universe and help us measure what we call the Hubble constant. Additionally, understanding both the gravitational wave and electromagnetic side of this, we can understand how neutron star matter, what the equation state of neutron star matter might be. And on top of that, we might actually also peer into fundamental particle physics by understanding if there is a graviton, what does it look like? And so multi-messenger physics is really huge for us as a field. And here in the bottom right, I'm showing a light curve, meaning the brightness of an object versus time of the gamma rays, which peaks here. And on the bottom here, I'm showing the gravitational wave chirp, which is also peaking around the same time. Unfortunately for us, we've only detected one binary neutron star merger. That is, yeah, just one. And so we are genuinely starved, right? So we as astronomers and astrophysicists, we have a lot to do. We have usually dozens of things happening at the same time. But we would really love for more data from a multi-messenger source. There's numerous programs that are looking out for this. And we have been disappointed so far. So what I work on is a more promising and a more common, hopefully, source of multi-messenger emission, and that is supermassive binary black holes. I'm going to abbreviate this for the rest of this talk, the rest of the 6 minutes, because it's too much to say. And we're going to start with a couple of axioms. So we know that galaxies host supermassive black holes at their center. Right? So we see galaxies and we see their central supermassive black holes, and this seems to be pretty ubiquitous across all galaxies. And we also see galaxies merging, right? We see this all the time. Throughout cosmic history, we see galaxies merging. And so it's a pretty simple leap to say that when galaxies merge, we also expect their central supermassive black holes to merge. And so we make the claim that, where am I? There we go. Supermassive binary black holes should form ubiquitously. And so on the right, I'm showing an artist's concept of what this might look like. And so we have a galaxy, a bright center, and if we zoom into that center, we see our binary black hole. Okay, so then the question becomes, if they are such a source of wealthy information, for lack of a better phrase, how do we find them? And so you could suggest we use bigger lasers. And this is a real thing. So the Laser Interferometer Space Antenna LISA is planned to launch in 2035. And we are going to put hopefully 2.5 million kilometer separated detectors in space, trailing Earth. And this will allow us to observe supermassive binary black hole mergers like never before. Or we could also use better telescopes, right? Traditional electromagnetic telescopes. For example, there are missions like the Black Hole Explorer and the Next Generation Event Horizon Telescope that could maybe take images of supermassive binary black holes that look like the Event Horizon Telescope images we've already seen. However, these are not online yet. They launch in like 2035, and I actually am not sure when I'm not sure if either the Black Hole Explorer or Next Generation Event Horizon Telescope has a launch date yet. So the question is not quite how do we find them? It's how do we predict what they will look like? And so this is where my research comes in, where we take numerical simulations and theoretical calculations. So we take our current understanding of physics at these extreme limits and apply them to supermassive binary black holes. And the goal here is to meet observations where they are today. And so there are observations we can do of supermassive binary black holes, but generally they are candidates, meaning that we don't really know if they're really supermassive binary black holes. They often look quite similar to single supermassive black holes. They have some periodicity, but we're not exactly sure. But the hope is with theoretical calculations, we can actually bring our understanding closer to where observations are. And so this is an image I think about pretty often. And it's this relationship between theory, what we already understand, and observation, what we see but maybe not quite understand yet. In reality, especially for supermassive binary black holes, this gap is quite big. And my goal and our goal in our field is to bridge this gap. And so now we can start to answer the question, what will these binary black holes, supermassive binary black holes, look like? Well, we know there'll be two of them, right? And when you want to understand black holes and orbiting black holes, you need general relativity. That is, you need Einstein's theory of GR. And they're in an orbit. But I also said that we need multi-messenger sources. And for black holes to light up, we need gas. And to describe gas, we need what we call fluid dynamics. And so these are the Navier-Stokes equations. Don't pay attention. That's just an example of some of the things we do. And so if we put these together, these are two of the things that we could help describe these binary black holes and accretion onto them. But in fact, the picture is actually so much more complicated than that. We have fluid dynamics, we have general relativity. Turns out magnetic fields are also really important. So we need Maxwell's laws, Maxwell's equations, and also radiation, right? There are photons everywhere. And unlike in our daily lives, these photons have a really appreciable effect on how things move and things evolve. And so we can consider having all of these physics in our simulations. Unfortunately, we have to be picky. We have to choose what we simulate. And so we stick to those first three and we get general relativistic magnetohydrodynamics. So we solve Einstein's equations for GR, and so we solve the fluid equations with magnetic fields. And so this is what we get. And so what we're looking at is a simulation that I ran a few years ago. We have our two black holes here, and they're going to orbit each other. With this color, you're seeing the density of gas, and I'm just going to let it evolve. And so we see these dense streams of gas fall into each black hole, circularize, and accrete. And so by evolving this system for many, many orbits, we could try to understand what these might actually look like. Cool. I could actually let this play forever. But in the interest of time. Okay. So in the simulations, since we simulate in 3 dimensions, we also have those relativistic jets. And so here on the left, I showed that picture of a galaxy with a zoom in picture of the jet. On the right, we're showing an XZ slice of the system. So previously, we were looking down at the system in the XY plane. Now we're looking at the XZ plane. So we're looking face on, or rather from the side. And vertically, we're seeing these large structures, these bright fluids, which is indicating the magnetization. So how strong the magnetic fields. And with the white lines, we're seeing the magnetic field lines themselves. And so we're seeing these large magnetic field lines. And we're seeing this kind of same structure, the same shape of the jet here on the left-hand side. And so this is a good thing. This is a known result. And then the question becomes, right, these movies are pretty, but what will the telescopes actually see? How do we meet observers and observations where they are today? And so now we need to model what the electromagnetic radiation or photons might be from these systems. And if I lose a few of you here, I apologize. This might get a little technical, but gas accretion onto each horizon is going to make the gas extremely hot. And hot things radiate like black bodies. You'll see this with your fires, or if you burn something on a stove, it'll get hot and it'll radiate. And so if I measure the accretion rate onto each horizon, so how fast are these black holes eating, I can also predict what the X-ray emission might look like from these systems. And so we see the accretion rate as a function of time, and it's peaking. It has this really periodic structure. And so we can make the claim that these black holes will emit X-ray emission with a very consistent periodicity. In addition to that, we have very strong magnetic fields. And when there are very strong magnetic fields, and they're also very energetic electrons, these charged particles will gyrate or undergo circular motion. And accelerating charged particles will also emit radiation. When those particles are relativistic, they emit what we call synchrotron radiation. And so we can actually predict what these jets are going to emit in certain wavelengths. And so I ran a calculation where we take the synchrotron emission and absorption coefficients and try to understand how this jet might radiate. And so what I'm plotting here on the y-axis is the luminosity. So that's how many photons are we seeing per second. Not exactly, but you can think of it that way, versus time. And so we're seeing these really clear peaks in the jet emission. And so to be more specific, this is for eccentric supermassive finite black holes. And so what we're hoping with this kind of work is that we're actually bringing theory a little closer to observation. If you see that change, it's a small change. But I want to emphasize there are hundreds of scientists working on this across the world. And so the work that I showed is just one example of how we're trying to approach this problem. And so there's a huge number of studies that make important contributions. So in the top here is a two-dimensional study of Newtonian hydrodynamics, which shows accretion onto a binary. Here in the bottom right is a recent study of 3D Newtonian physics, which understands these black holes in much larger separations. And we shouldn't forget that we've been building on decades and decades of work by previous scientists. And so this is a simulation from 2015 of a black hole neutron star merger. And one thing I really want to emphasize is that collaboration and diversity of approaches is crucial to progress we make in this field. And all in all, we're all kind of building towards LISA in 2035. So I just joined the LISA consortium, which is really exciting, and it's undergoing some changes at the moment. But it's a cross-continent collaboration, and so Europeans and Americans mainly are working really hard to get this mission off and going strongly. Obviously under the threat of the Trump administration cutting everything. I am really personally very excited for this mission. It's what I think is going to be the most daring space mission yet. And it's going to unveil a completely new window into the universe and how we approach understanding fundamental physics. And so I'm going to finish here. I'm over time, so I'm going to leave my conclusions on the slide, and I'm happy to take any questions.
Thank you again for such a wonderful talk. It is great. And also thank you for leaving this beautiful simulation on the final slide, because it's just so pleasant to look at. And I think that's one of the best things about astrophysics personality, and I might be biased about it, is how a lot of the science with this also aesthetically pleasing, which a lot of other science fields also have, but this just showing here. But I had a couple questions that I wanted to ask. One of them is about this. The one other example that I've seen about multi-messenger astronomy has been from supernovae being a combination of electromagnetic radiation and neutrino detection. I'm wondering if there is any possibility of any sort of also particle emission, perhaps neutrino emission or something that comes from, say, neutron star mergers, that could also add to a third layer of multi-messenger detection here with gravitational waves and electromagnetic radiation.
Yes, that's a great question. So in the case of neutron star mergers, neutrinos are expected to play an extremely important part. In fact, if you want to run a simulation of a neutron star merger, you really want to include neutrinos themselves, because neutrinos can act like photons and exert pressure onto gas. However, observing neutrinos from a source, from a binary neutron star merger, would be really difficult because that source would have to be very close. And so the only known multi-messenger detection that includes neutrinos are the supernova, supernova 1987A, I think, which was in a nearby galaxy or one of our satellites, and also some blazar candidates. Blazars meaning these supermassive black holes that you're looking down the jet of. And so, yes, it can add a layer, but I don't know enough about neutrino astrophysics, other than the fact that if we saw neutrinos, it would be like, okay, cool, we already knew that. So yeah, I wish I could say more.
And I can see that Attila has raised his hand. So any question or comments coming from you, Attila?
Yeah, actually, both probably. But so first, let's start with the question. So this is very interesting. Thank you. I learned a lot. My question is really like, so suppose we see, an oscillating behavior in the synchrotron flux, which, is very possible. How do we know that it's not just some, material that is orbiting a single black hole?
Yeah, that's a great question. And so what we're looking for are what we call smoking gun electromagnetic emission, right? And so smoking gun, I mean, a signal that could only be explained by one thing. And you're totally right. I don't think if we see oscillating synchrotron emission, I don't think you could reasonably say that that is only coming from a supermassive binary black hole. But if I can back up, if I ever get there, there we go. I think you would struggle to find this level of consistent periodicity in a black hole accretion flow. And so we do see like Sagittarius star flaring on some time scale, and I'm sure M87 too from like the magnetic flux eruptions from the horizon. But this level of consistent periodicity is, I would say, unheard of. Even then, if we saw something like this, I would say this could be a supermassive binary black hole asterisk. And I think what you really need are event horizon scale images or a gravitational wave detection to confirm them.
Yeah, so I mean, if I think of our galactic black hole, it's kind of an anemic black hole. It doesn't eat very much. So, like I guess, if you would have like a large molecular cloud or like a star cluster or something go near it and will start orbiting it would, it would have more periodic and larger variation. It's not, yeah, our galactic black hole is not a very periodic thing in general. So the other thing I wanted to say was a little bit about the neutrino stuff since it came up. So like I think that is a very hot topic for multi-messenger these days. And so we have these ice cube neutrino events where we detect neutrinos, and we can only kind of tell roughly which part of the sky they come from. And it's kind of the holy grail of multi-messenger astrophysics nowadays, to kind of pinpoint it. And because if you can pinpoint the source, then you can learn what type of source it is, whether it's a supermassive black hole or a neutron star merger or some other tidal disruption event or something. So yeah, it's a big question, and we hope to have an answer in the next couple of years.
Hey, so thank you so much for the question. I'd like to ask one personally. Keep in mind this is far from my field of expertise, but I'm still curious. So for clusters, the way I understand it, distance is usually measured using C-feed variables for stars that are outside of the range where you can use parallax. Now, depending on how much matter is orbiting these black holes, they're going to be, as you said, based off of the black body principle, they're going to be emitting a different type of light. Also, they wouldn't be pulsating like C-feed variable stars. So, is there a way to measure distance to these sort of orbiting black holes outside of the conventions, I guess?
Yeah. Okay, so distance measuring is hard. This is like the core principle of the entire field of cosmology is measuring distances. If I recall, Cepheid variables, they both have a well-known luminosity and periodicity relationship. And so that's why you can do a distance measure, because you know both the periodicity and then what its luminosity is supposed to be. With supermassive black holes, it's not as simple because its luminosity is also dependent on its mass, and its peak frequency is also dependent on its mass and the accretion flow itself. And so you have a few more moving variables before you can actually say anything confidently about the source itself and its distance. So it's a good idea. I'm not totally sure, but I see Attila's hands raised, so maybe he can add to that.
That would be interesting.
Well, I mean, so it is a difficult question, but actually one of the things that we that help us sometimes with supermassive black holes is that they have maser emission near them. So masers are like lasers but microwave, and so we can actually check the motion of them. So we actually can see them move, and from the motion and just using you can figure out either the distance or the mass of the black hole. So it's basically it's a degenerate problem, but it helps a little bit.
I understand. Okay, thank you so much. Thank you so much for answering it.
And I think I have one more question, unless anyone else jumps on the Q&A before we may move into the panel. But I wanted to ask about, so during your talk, you showed some plots that I believe were showing flux or flux density over time. And so we could get an idea of how much light is coming. The simulations are trying to give us an idea of how much light would be coming from these objects. But looking at, say, the two images that we currently have of black holes that we have spatially resolved with both MH7 and Sagittarius A star. Do these simulations that you're working on or similar simulations also come with some aspect of spatially resolved luminosity for these photons? And does it involve some kind of ray tracing or any other process for that?
Yeah, so this is a great question. And so this is something I am planning on doing with our binary black hole simulations. And so if I can back up a second, how we created models for the single supermassive black holes was you take the matter, you take the space-time, you say the electrons are a certain temperature. And if I remember correctly, you assume that the electrons follow some thermal distribution, they emit synchrotron emission. And what you have to do is when you get the emission at a certain point in space, you have to follow that ray back to a camera, right? And so that's what you call the ray tracing. And then along that way, you also have to do radiative transfer. So if I emit a photon in the disk somewhere, let's say like near the black hole, it's going to interact with material and other stuff on its way to your camera. And so you have to understand what it's doing. And so that's called a general relativistic ray tracing and radiative transfer. And so that's what people have done for supermassive black holes in the context of single black holes. And that's how you figure out what sort of accretion flow is around M87 star or Sag A star. And I would like to do something similar with these binary black holes. It's like a matter of time and expertise. But luckily for me, many of the people who work on the Event Horizon Telescope, both on the observational and theoretical side, are actually at the University of Arizona. And so that's one of the things I have a timer on because I want to do it before I leave. So yes, it's a great question.
And yeah, Attila has a hand raised, so go ahead.
I have another question. Sorry. It's very inspiring. Anyway, my question is like, so when you do this simulation, what happens when you put in spin for the black holes? And they can be aligned, not aligned, or what? Because the metric changes quite a bit if you have a spinning black hole.
Yes, so that's a great question.
Do you get very different results?
Yeah, that's a fantastic question. And so the question is a little more fundamental, right? So with a single black hole, we have mass and spin, and that's great. That's all you really need to describe these black holes. With binary black holes, the question is a lot more complicated. You have the total mass, you have the mass ratio, you have the relative spins, you have the angles of the spins. And so what you're essentially asking about is exploring the parameter space. So spin will change things. I will say that our simulations are fully from first principles, which means that we solve the space-time in real time, which means that adding spin or changing the spin is not difficult. It's just a matter of doing it. But due to the expense of these simulations, we keep things simple first by including no spin and equal mass ratios. And the idea is to build up to include spin. I do think things will change with spin. So first of all, you will have much stronger jets. And so when you have higher spin, you have more powerful jets. When you have spin, you'll also be able to sustain more matter in what we call these mini disks around each black hole. And so you might actually see more consistent structure depending on the separation of the black holes. And then if you tilt the spins relative to the accretion flow, then I think all bets are off. I think even some of the initial assumptions you start with, like your initial data for your matter, I think even then you have to consider, like, if you have a tilted spin, would that circumbinary disk even form at all in the first place? And so that's a really interesting question, and I hope to address it. But again, right, it's the constraints of time.
Well, thank you very much again to you, Vikram, and Attila, and everyone else who has joined us in this session. for this awesome talks. I believe from now I'm gonna pass it on to the rest of the chairs to move on to the panel. But thank you very much.
Okay, are we waiting for Shivam? Ah, yes. Yeah, so if no one else has anything, I'll maybe start. I just wanted to ask you guys in general about your path from UWC to your research in physics and how it went, and whether you have yourself any idea how to any insight on how we can connect physics with humanity. I'm a theorist, so I'm a bit disconnected, I would say myself.
Sure, I can start. So I talked a bit about my path at the start of my presentation. I took quite a linear one. I think what we say like traditionally linear, meaning I went UWC, college, straight to grad school. I also took breaks from academia. I worked in industry for a summer, something completely different in like consulting. And that was also an important experience to provide a comparison, like a genuine comparison of what your life would be and what other options you have. And I think if you're all here and you all went to UWC and you all study science, you will have many, many options. And it's important to consider what academia will bring you versus something in industry. And so that would be my advice. And getting into grad school these days is extremely hard. So if your path is not linear, do not be discouraged. That is not the end all be all.
Thank you. If someone else has anything to add, you can just grab the mic.
Sure. I've been speaking too much, but sorry about it. Yeah, I don't know. So like a couple of things about humanity. So first is that I don't think I ever foresaw where I'm going to end up, and I don't think you should either. It's go where the opportunities take you. So don't be fixated on some idea. And I think along that lines, I think it's much more important who you work with rather than what you work on. So I've seen so many people get burned because they were fixated on a subject and they ended up with horrible advisors. And that I would rather go with the good advisors, go where the colleagues are nice, because it's going to make all the difference. You will be happier. It doesn't matter where you end up. You will be happy that way. And the other thing with humanity that the other aspect is that I think one of the problems for us scientists is that we all love what we are doing and we are so sucked into it, we forgot to communicate with the rest of the world. And I think we are paying a little bit of a price for that, because I think the public is getting more and more disconnected from our research and not interested and not engaged. And I think it is up to us to bring it back to them, and we have to be able to communicate what we are doing and why it's important. And I think the UWC background is an amazingly good training for that. So please, do your best. Don't forget. You have to explain what you are doing to the layman, to the average people, and you should.
Thank you.
I'd just like to add that the current situation in certain parts of the world is pretty indicative of this sort of difference between what people working in these fields and your average Joe think about science. I just think it's an interesting thing to bring up. Of course, avoiding any political ideas there.
Yeah,
I
I guess
don't.
like
You should, you know.
yeah, I guess like on like that note, it's almost like even more important that people interested in science like just keep pushing science for science's sake and for humanity's development. Like I guess there's like a lot of noise in the world, but like ultimately, if we care about like logical things that develop our knowledge base that we can build on to do things for the world, and that is where we fall in the pipeline as scientists, right? Like we produce knowledge that can later hopefully add some positive contributions to humanity. And even if there are a lot of ups and downs and noise in the world, I think at least one thing and the baseline we can do is continue that work earnestly.
Just following up, since we mentioned certain areas of the world, particularly now we could say the US, I was actually wondering what your opinion is. Should I aim for a PhD in the US? It was like I mentioned maybe earlier, it's kind of my ultimate goal. But the situation isn't the best right now. To give some background, I did my bachelor's in the University of Helsinki, and I'm going to do my master's in Munich. Well, I'm curious to know if you're all in the US, but I wonder if you have an idea how the US versus the European system differ in terms of research, but also in terms of education.
And if we could keep this the more so perception of education or science rather than political situations, that would be very, very appreciated.
Yeah, I have thoughts. First, science is political because science is education, and so I think we'd be doing a disservice if we avoid that. But I will stay away from it, because there are bad actors out there who will want to not educate the public for their own gain, and so science is political. Everything is political. That being said, we are probably going to see like depending on how long funding cuts happen, if they happen, which it looks like they will, you're probably going to see like a brain drain from the U.S. And so I already know a bunch of people who are graduating from my department who are going to end up in Europe, both for funding and culture reasons. And so my short answer to you is stay in Europe and do your PhD in Europe, because every single department, no matter how rich or how well funded they are, is struggling with funding, and having funding pulled. And so you don't want that anxiety over you when you're doing your science.
Yeah, I think I would like to add a little bit on that. As someone who just went through the process of applying to graduate schools for PhDs in the US in this year. And to put it in perspective, I applied to 10 PhD programs here in the US. 8 through 10, something like somewhere in there. And I got rejected from all of them. Some waitlisted and then rejected, some immediate rejections, and all of that has been told to me to come majorly from the funding limitations. A lot of departments I've heard have had to fully limit to fully pause PhD admissions or limit it by 50% or more than what they originally planned. And so as a piece of advice as someone who applied mostly just in the US, and then now I don't have a PhD graduate school to go into this coming year, I would advise to still apply to the US if that's your goal and that's interested for you and you see programs that really call for you, but having non-US options that you can apply to as well that would still be good fits. Because yeah, the US currently has a very limited intake of PhD students.
I'd like to personally ask, as somebody who, well, to whom this is very relevant right now, as somebody who is yet to graduate from UWC and go into college. So even before the start of this year, let's put it that way, I noticed that many people have this sort of, well, maybe that's what I'm gonna ask about. Irrational bias about like universities in the U.S. I think everyone, especially at our UWC, is sort of, well, at least leaning towards that. I'd like to ask if what you think about, of course, not about the funding aspect of it, but the purely educational side of universities in say Europe, or maybe I know some of you went to universities in Singapore, so that would be an interesting one to talk about also.
Okay, I'll say something.
Okay, yes.
Actually, like, I'm somewhere in between, because actually, so I'm officially on paper in the US, but I actually live in Germany, and my wife is actually a professor in Germany. So I kind of see both sides of it. And I think there's two parts. So the first part, that I think for undergraduate education, it's less affected by the funding cuts. And I think you have great professors in the US. And in fact, but you can also get very good teaching in Europe. I do see that, my wife tells me, because she's teaching at a university in Bonn, that a lot of the professors in Europe are much more old-fashioned. So, they have been lecturing the same way for 30 years, and you often end up with them. I think the US is a little bit more dynamic. So you get much more cutting edge, more up-to-date material. The presentation will be a little bit more fun. It's going to be less dry lecturing. It will be more engaging. So I think there is still room for going to the US if you're not bothered by the politics.
Right, of course. I'd like to ask.
Still, also I think there's great opportunities in Europe too.
No, of course. I mean, there's plenty of great universities. I'd like to ask about because we have Shivam here about Singapore and Vikram also. I'm pretty sure both of you went to Southeast Asia, right? So I'd like to ask, to my understanding, you were not very familiar with the well, you moved to the U.S. right after UWC, but still, I'd like to ask, what do you think about education in Singapore?
Well, I mean, yeah, and US is a very like well accredited school, and it's like I have some friends there who really enjoy their time. I think it depends on the program there. I know computer science friends have really enjoyed. Some other engineering friends have found it a bit too competitive and regimented. So it's like really depends on person to person. I will say that like they have a like more 4-year like US program style. So you can like I think you can switch around more than let's say the UK and other places. Just because the one thing I appreciate about US education is that you can a lot of times you can change your major throughout the time and you can take classes across different fields. So I think they have something similar. I'm not sure if the same level to the US. But yeah, I would say for the STEM, I think it is very strong. I think the one advantage the US has for now is that people from all areas of the world come together there, which is a very unique thing. I'm sure it happens in Europe as well, but I know that it happens less in US from like the number of countries that people come from. And that's something I appreciate a lot from my education. So those are things to note, but I think it's a great education still.
Thank you so much. Thank you so much.
I can share a little bit because I did a semester abroad in the UK while I was in college. So there's a little bit of a kind of compare and contrast there. So I think, like I was mentioning a little bit before, in the US, you do have, like, at least in my institution, we do have very, very good quality of teaching. The style is a little bit different. So in the US, one can say it is a little bit more like spoon-fed a little bit, not in a bad way per se, because sometimes because the professor does a lot of work to really prepare the lectures for you, and they're good at that. In the UK, I was a little bit thrown out of the water because, well, the lecture was very much like the professor gets up there, talks for like 15 minutes or an hour, even longer. Sometimes you go home, you do your homework by yourself. You get 1 month off before the exam. So you study everything basically in that month to do the exam, and the exam counts for everything in your grade, which is very different compared to the US system. And that was very different. But actually, I surprisingly learned something, which is the ability to read books and just learn by myself. And that actually is a very different style of learning. It ended up helping me in my grad school, because that's something you have to do a lot in your grad school as well. But I'm just saying that there are like these different styles of teaching, and they teach you different things, but you do need to consider like what kind of learning is more suitable for you. And I must say that like the UK system worked and helped teach me something for one semester, but I would not really enjoy it as much on the scale of like having more, mentorship and kind of help and other kind of experiences outside of the classroom, since the professor was not as engaged in that. So yeah, of course, again, it depends on the institution, and the institution in the UK I went to is, of course, the bigger type, not the liberal arts type. But these are also kind of some differences that you can think about. But either way, I think all of these different institutions are very strong in a lot of different ways. And I think the US, for me, one of the biggest thing it offers is actually the ecosystem, like people have been mentioning too. There are many people from all over the place comes together, and many, many brilliant minds and people who are very committed to this work. And the ecosystem is something that really can help your research or your whatever interest go very, very far, because you have people to work with. That's, for me, is the most important thing about the US right now. Of course, you can say that that trend is now a little bit declining if people are leaving the US, finding that this is no longer a very favorable place to work. So that might change in the future, and that's what we should be watching out for in terms of deciding where is the best place to be. But yeah, for me, if I have to say why, one should choose the US, is probably because there are a lot of good people here working on, like, a lot of leading research, and people who are very committed to doing these work, despite whatever the political situation is.
So it's kind of like a self-fulfilling prophecy. Basically, people go there because there's already people that are there that are good. So people perceive it as good, and that's what makes it good. But the question is, given the status quo, this could, as you said, change in the future. So I don't know. It's just something that I've been
Sorry,
thinking
just
about
a note
recently.
on the status quo, because I also wanted to add previously about the funding cuts. Just a caveat is that, at least for now, I mean, like, just I guess, pluck from my field, but it's like I'm pretty sad about the science field, but for quantum, NSF has said that they're not doing any funding cuts, and like a lot of the quantum ones have like private funding as well. Obviously, everything is variable. I would say on the quantum side, you can still like bet that there will be investment for a while, because it's a national security concern as well for them to build a quantum computer. And then a lot of quantum theorists can also kind of twist their work into fitting into that mold. So there are like ways, like some research areas can, like quantum optics, all that whole field can be put under that, and the funding is a bit more stable there. So if you're scared about funding for that field, I would say less so, but like I said, it is variable. And also a presidential term is 4 years, and your PhD is 5-6 years. So yeah, we'll see.
Right, and yet you still wouldn't want to get kicked out of the country for absolutely no reason, of course. I think it, oh, I don't know. It's just something to think about, of course. But as you said, I think many of the more so physics related stuff are applicable to the national security, so maybe cuts won't be that severe there. Rosario, I believe your hand is up.
Yeah, I wanted to step in on the conversation. I was actually one of those people who thought that the US was overhyped, and that maybe the teaching of physics would be less rigorous than in Europe, particularly in Italy. And I ended up really regretting not applying for the US. So I haven't been there myself, so maybe I'm wrong, but I have been on semester at sea, so I had the opportunity to interact with mostly US faculty. And like they've said, like the other speakers have said before, they tend to be much more engaging, a bit more young, let's say. And the approach is generally quite different. So one of my favorite teachers is Canadian, but teaching in Helsinki. Like one thing he said is that the European system tends to be more focused on theory from the very beginning, while the American one, not North American, maybe even UK, tends to be a bit more heuristic. And for me personally, having a bit of a better intuition at the beginning and then going on the more rigorous theory works better. We definitely go much more in depth in the mathematics, for example, in Europe in general. One thing I didn't like about Europe, just to say another thing, for example, was that we end up having our own teachers' lecture notes that we have to read, while in the US, they have internationally recognized textbooks that are generally much, much better. So I often found myself being very annoyed because I had to read crap lecture notes, and I just wish the lecturers followed, you know, an American textbook instead. So yeah, and in Europe, if you apply for an English-speaking program in a country where that is not the main language, which is most European countries, I recommend you ask maybe someone who's someone who's a physicist already to give a look at the program, because I now can easily tell just by looking at the program I enrolled in that is terrible for physics. But when I was applying, I had no idea what Lagrangian mechanics was, and I didn't know that it was really bad that a physics program didn't include that. So yeah, I would say maybe the US. My perspective is that the US deserves its title as a place where education in physics, at least, is better than Europe.
That's very nice to hear from somebody who's experienced well, education in Europe. I can personally say that I live in Europe, so I have heard of professors basically forcing you to buy their books so that they can well, give their sort of notes, as you said, which might be
That
something
happens.
worth considering.
That happens everywhere. Everyone wants you to buy their.
Okay. Well, never mind then. Yes. Sure. Fine. Yeah, thank you so much. Thank you so much for answering this, Rosario. I'll definitely consider it, and everyone from the audience should probably consider this sort of aspect on things also. Thank you so much.
With that, I would like to move on to another question that I was really excited to ask, and I acknowledge that it may mostly be applicable to Attila and Vikram as astronomers or astrophysicists, but you know, it can be rephrased in a more broader context, and also if you feel like it applies to you, feel free to answer as well. But given the history of settler colonialism and how science, and in this context astronomy, cannot be separated from the people doing it and the people that it affects, how do we as a scientific community address the history of building facilities in lands that have been irresponsibly appropriated, the likes of the controversial proposal for the 30-meter telescope in Mauna Kea? And if you can think of any examples or ideas of how astronomy or science at large can collaborate rather than appropriate with the land and the people who inhabit it.
Sure, I go first. Since I've been, living on Mauna Kea, scientifically speaking, it's been contentious for 30 years, and it's been kind of the volume has been turned up more and more. I think a lot of the blame goes to the early telescopes that went there that did not give the respect to the native communities as much as they should have. So they were always involved. So for Mauna Kea specifically, there is a Council of Elders. So it's a group of Hawaiians who represent the Hawaiian culture, and everything was always done in consultation with them. But it was not enough. And actually, in some cases, the council did feel that they were cheated. So actually, my telescope, the 7-millimeter array, is actually one of the ones that really upset them, because they gave permission for a telescope, and nobody explained it to them that telescope is 8 antennas. And so when they saw the 8 antennas, they were very, very upset. And they said, we didn't give you permission for that. And they were like, well, it's one telescope, but that's not how they see it. So I think that was a big problem. Another big problem is, the Mauna Kea is actually also very sensitive, because they have burial grounds. So the Hawaiians have buried their nobility on the mountain for centuries. And actually, it can happen that you walk around there and you bump onto human remains. And that was also not dealt with very sensitively. And so the 30-meter telescope is a total disaster, and I really hope it goes away. I mean, I think the telescope should not be built, in my opinion, but it might not be enough to save the others. So my old telescope, the CSO, was basically given up as part of the peace offering. So they said, okay, we will remove some of the telescopes to make a compromise. So I think it's a bad case, and I think it really needs better communication. On the flip side, these telescopes have really brought to Hawaii a lot of know-how and engineering jobs and high-tech jobs that didn't exist there before. And I don't think it's being stressed enough, and people, the Hawaiian community does not recognize that as much. And I see the big difference to Chile, which is another place where I have been working. So, Chile has embraced that wholeheartedly. And so, since 20, 30 years ago, when astronomers really started to move to Chile, Chile has really benefited from it because they actually grew up a whole generation of engineers that were not there before. So actually, Chile is now a powerhouse of high-tech engineering and making devices in astronomy. And yeah, I think that's they're two different worlds, and I think in one case they did it well, and in the other case they did it horribly.
Yeah, I don't
That's
have much.
my 2 cents.
Yeah, I don't have much to that. I think that covers a lot of things. I can talk about what we do here at the University of Arizona. Arizona is home to many indigenous nations, and I think the astronomy community here has done well, not to just consult with them, but to include them in our science. And I think that's the biggest thing. And so we have many programs that engages directly with indigenous communities and indigenous leaders. To actually be a part of our science. And so this is a collaborative effort, not something we're doing with permission. And I do think that's the way to go. And then if I can talk about something that's coming up, which is I believe it's called the Einstein telescope. I always get it mixed up, which is a next generation gravitational wave interferometer. And I know that someone here at the University of Arizona, Kate Daniel, is on the board, and she is both indigenous and also leading the division of that telescope that is directly communicating with indigenous leaders and indigenous nations, to make sure that wherever we put this telescope, that we have both not just the permission, but with the support of everyone who is from that land. And so I do believe inclusion is the way. And yeah, I thought I heard rumblings from Chile that indigenous populations in Chile were also somewhat upset, but I don't know if that was more recent or more minor. That was also in passing. I heard from people who use the Magellan telescopes, but I don't know.
Yeah, I think the optical telescopes are in a more inhabited area than the millimeter wave or sub-millimeter telescope. So, at the high desert in the Atacama, there is nobody lives there. So they, it's not sacred site or anything. But you are right, like Paramal, that's probably a more sensitive area.
Well, thank you very much. Yeah, it's very insightful answers. I think it puts a lot into perspective on both when things are going well and when things are going wrong. So we hopefully can move towards doing things right. And we're almost at closing stages. We are kind of over schedule. So we just wanted to ask one more quick fire question. And is if you all have any book recommendations that you want to share with the audience here. And it can be, nonfiction science book, but also your favorite sci-fi novel or anything that you want to share. I can give an example and go with mine because I already had it ready, so I'll give you time to think. But I would recommend The Disordered Cosmos by Dr. Chanda Prescott-Weinstein. I have it right here with me, but I don't know if the background will block it. I think it's a great book for anyone interested in physics, particle physics, cosmology, and also thinking a lot about physics connected with humanity and how we cannot separate the science from the scientists. So I just wanted to push that. It's a great book. Highly recommend it. Anyone else, feel free to share your book recommendations.
I can recommend. Oh yeah, you wanna go first? You have it in your hand, right?
Yeah, I just grab it from my bookshelf as well. So yeah, I have this book by Bill Bryson. Let's see if it can actually show up. A Short History of Almost Everything. It's a pretty thick book, but it's actually really funny. Bill Bryson is one of my favorite writers ever. And it just goes through a lot of scientific stories about how we find out different things about the Earth. So not just limited to physics, but it's a very fun book if you ever want to have a light-hearted read on science.
Yeah, I can recommend When We Cease to Understand the World. It's also, I think it's by a Chilean writer, yeah, Benjamin Labatu, if I pronounce it right. But it's also a very interesting book about historical scientific figures, and also how you can't separate the science from the scientist, and also how science has the power to do great things to the world, and great both in a good way and in a bad way. So I think it's a very sobering book and a very important book to read, like the responsibility we have as scientists, but also kind of how often the creations we do can go into the wrong hands, but we'll see what we can do about that.
My go-to book recommendation is When Breath Becomes Air by Paul Kalanithi. It's not a science, it is, well, it's a science book because he's a scientist and a doctor, but it's very much a human story. Bring tissues for when you cry if you read that book.
Okay, I go last, I guess. So my favorite book is, I'll start with a bit of introduction. I hated textbooks, every single one of them. I think they are horrible, except one, which is Landau and Lifshitz Mechanics. And I loved it because it's thin. It's it's one of the thinnest textbooks I've ever seen, and it's the penultimate Bible to classical mechanics. And it's extremely dense. You can't read it. Like, it's not, you spend staring at each page for hours, but everything is in there without a single wasted word, which is why I love it.
If I can, though, don't read it if you're like a first year or second year student. It's pretty advanced. Maybe go for something like Taylor. I like that book a lot. So. Yeah.
Thank you so much, everybody, for your amazing book recommendations. It has been a pleasure chairing here with Rosario and Brandon and having all of you as our guests. But I believe, as Rosario already mentioned, we are slightly out of time. So if you guys would like to come watch our live stream tomorrow, the same time, that will be very, very appreciated. And I think we can wrap it up now. Thank you so much. It's been a pleasure.
Thank you so much. Bye.
Thank you.
Thank you all.
Thank you.
Thank you, Brandon. Thank you, Brandon. That was good. That was good. Okay, let me